Recording in progress.
Boiler tube leakage, its mechanisms of failure and preventions. इस वर्कशॉप में आप सबका स्वागत है। जैसा कि आप सब थर्मल स्टेशन से हैं, you all know the importance of boiler, and boiler failure is the main cause of loss of availability, because once the boiler tube failure is there, it is depending on the area of failure and the type of failures. It takes time, and it's a long time also. And this is particularly very critical when we talk about the present day supercritical boilers, where the metallurgy is such that treatment time, pre-welding, post-welding is very high. So it is affecting our generation, it is affecting our availability and everything. And ultimately, in terms of JPL terminology, the cash score. So it is, this workshop is being organized by JIPT to have deliberations on these issues, which will help the industry as a whole to improve on the availability of our boilers, and so the units and availability of the power to the nation. So with this context, we have organized this workshop, and all the senior persons on the dais have the very big lot of experience in this field. Chaudhary Sahab and Singhania ji and Umar Ali ji in the boiler field for a long time. And from IIT Bhilai, Gangopadhyay sir is having a lot of experience in mechanical things and related developments. So from the academic perspective also, we will be knowing these things, and where the institutes of repute like IIT Bhilai can help us in improving our boiler performance and boiler availability. So with these words, I once again welcome you all. Thank you.
Thank you, sir. Now I would like to humbly request Mr. Dilip Kumar sir to grace us with a few words.
Good morning. So my friends on the dais, Chaudhary ji, he was my boss also. Manish Johari ji is our colleague. Umar Ali ji from L&T with respect to ultra supercritical boiler. Gangopadhyay ji will give us insight into the design aspect of the boiler. All my dear friends. So boiler tube leakage, I think sometimes it becomes a very known word. For example, it has become now in JPL. So its concern in the commercial unit is much more than the other units, because starting loss and whatever we are losing in days, straight away money loss. So what we want, no leakage, good performance, more money. That is the objective of our running the plant, and that should be our objective. So the question comes, I think young lads should come, the question should come in their mind, why tube leakage? होना क्यों चाहिए? आता होगा ना क्वेश्चन, मतलब डे टू डे लाइफ में वी आर रनिंग सो मेनी थिंग्स, बट कोई ऐसा ब्रेकडाउन रोज रोज तो होता नहीं है, तो व्हाई द ट्यूब फेलियर? तो वी शुड अंडरस्टैंड कि भाई लीकेज होता क्यों है, व्हाई? नो डिजाइनर शुड डिजाइन ए बॉयलर फॉर फेलियर. Should anybody will design? So still a failure takes place, then what is the reason? Somewhere manufacturing is the reason, somewhere maintenance is the reason, somewhere operation is the reason. But I think in most of the cases, designer never design a boiler for failure. So from that context, we should understand and we should try, we should see our aim should be zero tube leakage from overall to overall. That should be our aim. And we have to work for that. So we will discuss. We will not give any lecture, first of all. It will be an interactive section and you have to react, you have to tell, you have to interact. What are the reasons you think? Don't be afraid of asking any question, because don't think कि भाई मैं क्या पूछ लूंगा, कुछ अच्छा नहीं होगा. Nothing. Don't afraid of anything. Openly you discuss, clear your all doubts, and it will be an interactive session overall. Thank you.
Thank you, sir. Now I would like to humbly request Mr. Umar Ali sir to share a few words with us. Give me a good place.
Good morning, all of you. And thank you, sir. Vinod sir, Johri sir, and Bandhavadhyay sir, Dilip sir, and all of you for calling us here. So today, as Dilip sir told, boiler tube leakage is a very challenging market, and also it is a very commercial loss. So I am basically from L&T MHI boiler, where the manufacturer of supercritical and ultra supercritical boiler, and also supporting for all spare services and during maintenance, RLA, and all these things. So today I will discuss in detail about all these things, right from what we are, then what are the challenges in boiler tube leakage, what are the challenges with material, what are the challenges in the dissimilar welding, especially between your Super 304, that is very challenging in welding, with P92. This is very interesting. And what solution analysis is required for this, means heat treatment is required. Then I will share some live example also, means what problem we have faced in the industry, that also I will share. So thank you very much again. Okay, thank you.
Thank you, sir. Now I would like to humbly request Mr. Dr. Soumya Gangopadhyay, sir, to give up some few words.
A very good morning. The distinguished dignitaries sitting on the dais, the guests sitting here, and all dear participants. I am Dr. Soumya Gangopadhyay from IIT Bhilai. So I am very happy to Director JIPT and Katreji for kindly inviting us to attend this workshop. As my colleagues have already told, that this is going to be very intriguing session. I mean, the experts, eminent experts from the industries like JPL, then NTP, the various failure mechanisms of boilers. And just like you, we would also like to learn from the experts what are the various failure mechanisms, I mean, what are the problems that is being faced by the current industry. And myself and my colleague, Dr. Purnendu Das, has come from IIT Bhilai. So just to understand the various mechanisms of particularly corrosion, we have some expertise working in the field of wear and corrosion at various levels for various applications. So our interest is to understand what are the root cause of corrosion, how this corrosion can be prevented to prevent boiler tube leakages and other failures taking place. We, we have a short lecture where we would talk about various problems and the solution that can be undertaken by IIT Bhilai to tackle or address the problems of boiler tube corrosion. So I hope you will enjoy the entire session today, and the way we will also enjoy, like you. And thank you all. Okay, have a good day.
Thank you, sir. Now I'd like to humbly request Mr. Vinod Chaudhary, sir, to give us some few words. Give us some up, please.
Good morning. It is a very good initiative taken by JPL to have workshop like this. And it is good to have a workshop on specific topics like BTL. And I would suggest Munish to have many more such workshops in different areas of power plant engineering. Like in boiler itself, you can have on mills, you can have on air preheater, you can have on valves, and you can have on turbine, generator, GT, all the prominent equipment which we have in our power plant, we can have separate workshop on all such equipment. And it is good to have a workshop like this, small gathering, specific topic, people who are really connected with the subject are here to participate. It is good to have this kind of workshops. I thank JPL and JIPT both for organizing this workshop. I will talk a little bit about power sector. You know that India has already become the most populous country in the world. And many people will think that it is a bad thing. But I will say that it is not a bad thing. To have population is not a bad thing. Only thing is that this population has to be utilized in constructive work. And for that, country needs to develop. And for developing country, we need a lot of power. Currently, power growth is to the order of 7 to 8%. But the way our population is increasing, power growth should be of the order of around 14-15%. That means power growth is an indication of the development of the country. If it is currently increasing by 7 to 8%, you can understand that our country is growing at this rate. Because only when the country grows, only when the industry grows, only when the commercial activities grow, you require power. And if the power growth is of the order of 7 to 8%, that means our country is growing at the rate of 7 to 8%. Tomorrow, if the power growth increases to 10%, 11%, 12%, you can understand that our country is also growing at the same pace. So power is very essential for the growth of the country. Now, if you want to employ this entire population of the country, then our country needs to grow at a rate more than 10%. Then only we will be able to give them employment. Otherwise, this manpower will be utilized in destructive work, negative work. So even with 7 to 8% of power growth, which we are seeing, it is a big challenge for all of us to cater to that requirement. Now today, when power demand has increased to the extent of 2.25 gigawatt, there has been power cuts all over the country. Now, where comes the relevance of this topic? The relevance of this topic comes from the fact that we have committed certain power to be supplied to some sector, and suddenly there is a power cut. So we are failing. We are failing in our commitment. So we have to meet our commitment. If we have promised certain amount of power to be given to the grid, then we should stick to it. That is why this topic becomes very, very important. And outage of boiler directly affects the outage of the unit. So if boiler is out, unit is out, power supply is cut off. That is why BTL becomes very relevant. Now, there are other equipment also, which is responsible for the outage of the unit. And we need to concentrate on those equipment also. BTL is not a very big thing. I'll be covering in my presentation. We are unnecessarily attaching a lot of importance to BTL, but BTL is not so much important. And you can see that BTL can be controlled in a very, very simple way. So I welcome all of you for this workshop, and I wish that all of you participate actively in this workshop and try to discuss out your problems and try to get a solution from this workshop. Thank you.
Thank you, sir, for gracing us with your valuable words. I would like to request Mr. Radhikati, sir, to present us with a thank you note. Please, sir, please.
Good morning to all of you and welcome in this workshop. Respected Vinod Chaudhary sir, Dilip Kumar sir, Soumya ji, Umar Ali ji, Johri Saab, my friends, all the HODs, sub-HODs, students. Really, I am overwhelmed with this response to the workshop. This is the third workshop in this series. As Dilip sir and Chaudhary sir told, there should be workshops or a discussion on the important topics of the thermal power plants. With this, this was initiated by the our ED sir, Singh sir. Always he emphasized on the learning and sharing of the knowledge. And with his inspiration, we have started these workshops. These are the monthly workshops. Earlier, we have taken workshop on the coal, then analytics and digitalization, and this month is the BTL. Really, it is the very good sharing, good knowledge sharing for us. And participants are from the power industry, expert of the domain experts, and academicians. It is the industry academic interaction. And really, it is very useful for us to share the knowledge, to share the experience, and synergize ourselves. This workshop is a full-day workshop, and there will be 7 to 8 sessions. First, there will be presentation by the JPL. It will be the case study of JPL. Then there will be presentation by the Vinod Chaudhary sir. Then after that, there will be presentation by the IIT Bhilai. Really, it is very good initiative, and I am thankful to the IIT Bhilai, its management, that they are ready to collaborate with us, with the industries, and it will be helpful to all the industries. Then there is a lunch break. Lunch is arranged in our JIPT hostel. After that, again we will assemble, and there will be presentation from JLUB Jharsukda, then DCP Donga Moha, Adani Raigad, then by L&T and Dilip Singhania sir. After that, there will be the concluding session. Really, I'm thankful to the participants. Participants are from the DB Power, then OPGC Bhelpahar, Adani Raigad. These are the physically present, and so many participants will join online. really, we know that we understand that there is the limitations to the physical presence, but we can participate online also. That's why we have initiated this hybrid mode. Once again, I am thankful to the participants and our guests to enlighten us. And I hope that this complete day will be very useful for us. Though there are few presentations, but we all of us can interact in this conference, in this workshop. And this workshop will be very, very interactive. Thank you very much. And I request all of us to assemble for this high tea. Then the regular session will start. Thank you. Sir, please. ये बाहरी हाई टी का प्रोग्राम अरेंज किया हुआ है, प्लीज.
आया कि नहीं तेरा
Ji, for the presentations. And after the presentation, there will be questionnaire session. जैसे जब सर ने बोला था कि आप कुछ भी पूछ सकते हो, जिसके दिमाग में जो भी आती है चीजें, वो आपको क्वेश्चन करना है। हो सकता है कि हमारे जो प्रेजेंटर्स होंगे या फिर जो साथ वाले होंगे, वो आज आपके जो प्रश्न रहेंगे उसका जवाब नहीं दे पाएंगे, लेकिन बाद में शायद वो क्लियर हो सकता है यार। दैट मे बी द इनिशिएशन ऑफ द सॉल्यूशन। इसके साथ ही आई रिक्वेस्ट राजश्री जी एंड मंडल जी टू डिलीवर द प्रोजेक्ट। थैंक यू वेरी मच।
Good morning, sir. Good morning, all of you. Today we are here for learning something on boiler tube leakages. We have some running practices as well as experts recommendations. Based on that, we are continuing developing best practices, implementing new things in our day-to-day overhauling activities and in the opportunity shutdowns. So we are here just to present what the kind of problems we are facing during in our BTLs and how we are rectifying, and some of the action plans which we have planned in our overhauling activities and in the long terms for the rectification of all these. So not taking much time, and I'm starting just presentation that what kind of failures we have experienced. It is rather than not more the numbers, it is more about the type of failure and the zone of failures in which we are facing the problems, mainly which kind of failures we are experiencing and how we are rectifying in the coming opportunities overall and others. So these are some statistics of our failures. Yeah. One second. This is some numbers that since 5 to 6 years back, we are having from data from FY19 to FY24, the year wise and the zone wise and the root cause wise, means the type of failures we are experienced in the zones, as well as type of failure mechanisms and the root cause of particular failure in the zone. So these are some numbers. We have initially, I'm just explaining that we have two stages. One is 250 into 4 and another is 4 into 600. So we are just saying stage 1 is 250 into 4 and stage 2 is 4 into 600. So this is stage 2 statistics of failures in last 5 to 6 years. Moreover, this is the zone of failures and the percentage of failures. That mainly we are facing erosion kind of failures. The more 49%, approximate 49 to 50% failure is because of flue gas erosion. Second major erection weld joints failures we have experienced. Third major failure is 18% around attachment failures. Other failures are considerably low, but from that also we are facing forced outage, generation loss. This is stage 1, 250 unit. And this is around 35% flue gas erosion failure in stage 2. Attachment failures 23%, joint failures, erection weld joints is 17%. So these are the major challenges we are facing in our boilers, and due to which our BTL experience forced outage around 40 to 50 hours in every BTL. We are losing the generation. So based on these failures, we have taken some actions, and one of the major that challenge or failure pattern The third, uneven expansion, scallop joint failures, the weld gap and all this. So based on all these failures, we have taken the measures to inspect in the overalls. Also, we have a certain 3.5% excess oxygen criteria in general operation practice. But nowadays, as recommended by sir, we have controlled and limited on 3.1%, and it is quite smooth. There is no such issue in facing for the operation for maintaining 3.1%. We have zone-wise inspection schedule in the opportunity shutdown as well as in the overhauling. Application of plastic refractories in burners in screen tube and arch area to control the erosion, in particular screen tubes and burner section. 360 shielding, left and right side shielding of 2 coils. Mainly, we are experienced the BTL in extreme left and right side of economizer and LTSH coils. So we have started that complete shielding of extreme left and right side coils to protect from erosion. And initially, the top tubes are shielded, but now we have experienced that number of failures in T2 and T3 tubes also. So we have a plan to shielding up to T5, means top 5 tubes we can shield so that we can have a less erosion on the top side. Coil alignment, one of the major factor to erode the tubes in the subsequent lower side. So we have a complete inspection as well as alignment in the economizer and LTSS side, and the locking, because we have done the alignment and after sometimes it will misaligned again. So we have locking arrangement in the bottom side as well as at the top side. Wire mesh fixing and the fixing at peripheral area of top coils so that we can that extreme left and right side from steam cool wall to coil, there is a certain gap in which the velocity is high and chances of erosion in the extreme left hand side right side is more. So in that particular zone, we have a plan to fix wire mesh to reduce the flow velocity, to control erosion or minimize the erosion. Similarly, we have some actions in the attachment failures, expansion movement of hot and cold conditions, bug stray movement and freeness. Sometimes we have faced the BTL in the burner attachment zones, corners, where generally bug strays are locked or somehow locked in the running condition due to chokage and ash ingress and all this. So this is one of the action we have planned to check free movement of bug strays at the corners and the support scallop attachments. We have faced 2-3 BTLs due to scallop section. So this part also we have planned to inspect scallop joints area, and where the scallops left over at the middle of the tubes, it was suggested that it should be up to the end of the tube, where around 180 degree of tube is covered with the scallop. But in sometimes at the end from 20-30 degree, it is not properly welded. So in the expansion, it will lead to tear off from the parent material with respect to the scallop joint. So this we have inspected and rectified in few units. In the upcoming overhauling, we have planned all these. Boroscopy of headers to inspect any foreign material inside the headers from the beginning or in the maintenance, due course of maintenance, that to remove, to avoid blockage for overheating kind of failures and all this. Stub joints, we are facing some failures in direct failure of stub joints, that is erection welds or shop welds. So we have planned MPI of those joints so that we can identify if any crack or any damage is there, so that we can rectify. Overheating, thermal fatigue, stress corrosion cracking, such failures mainly we have experience in reheater and superheater sections, mainly divisionals, inner loop, where skews bands are there, that radius is very small, and the bending stress as well as the thermal stress can experience during the operation. So these we have done the UT and DPT for all these bends, and based on observation, plan to replace all these. Oxide layer measurement, oxide thickness is one of the major reason to experience the overheating kind of failure in reheater sections. So IoT, and based on IoT's report, we have planned for replacement of all these kind of tubes where high deposits inside oxide layers. That operation, few points that in the BTL, we are generally saying this is because of operation, this is because of maintenance. So this workshop is mainly not to blaming operation or maintenance. We have to learn how to improve from this kind of failures. So some of the operational controls also we have taken in our slides, that coal GCB and all, as because we have a certain design criteria, but we are unable to operate within the design. But we have to restrict our operation with certain near to design limits. So these are some operational measures that as GCV and as percentage within the design condition, gradual ramp prep, because we have a loading pattern in high and low, but we have to be maintain the ramp rate so that the cyclic loading and stress due to this load operation can be minimum. Oxygen monitoring and operate at 3.1% as excess oxygen. Online monitoring of water chemistry, mainly these water chemistry parameters. We have both kind of sampling, online sampling as well as offline. So main focus to control the water chemistry parameter with respect to online analyzers, so that based on these, we can have a control on water chemistry. Steam quality, boiler cooling and startup as per design conditions. A few photographs that we have a failure, like erosion failures, stress corrosion cracking in the divisional section, some of the erection weld joints failure, specific some air ingress point in the ash panel area where some plates and this left over during erection, or in the running it will somehow missed. So this kind of failure we have faced. Some of the stubs weld joint cracking, which is in the erection itself, or erection weld joints failure. Some of the failures is because of flue gas erosion, fly ash erosion and all. These are some photographs that we can relate from your problem, that what kind of failures we are having here. Some of the control measures, controlling boiler tube metal temperature nearer to design operation with respect to operation control, soot blowing, after soot blowing, the lens is in home position, not in the extended condition. For the steam erosion, periodic checking of SADC tuning so that metal excursion can be minimum, periodic LRSB operations, wall blower, providing protection shields of top side of eco LTSH and other vertical sections, which we have measure erosion pattern in the failures, maximum percentage of tube thickness in every overhauling, so that each and every corners of tube can be analyzed with respect to the condition of tube. Water chemistry parameters, periodic checking of mill fineness to avoid secondary combustion or delayed combustion, as the mill fineness is the good range of design conditions, so that the combustion is very optimized or optimum condition, to avoid secondary or delayed combustion at elevated condition, to avoid overheating and other. Placement, CAVT testing and installation of CAVT screen for erosion protection, upgradation of tube material from 22 to 91 or SS347, HVOF coating and Canametal coating application in burner area and water wall near soot blower zones, so that erosion can be minimum in these zones. Installation of oxygen grid for better measurement of oxygen for optimized operation. This is some O&M control measures that suggested by Dilip sir in last few meetings back, and we have started implementation on those points, that every BTL, after BTL, we have a process of hydro test. But it was suggested that every time if we are doing the hydro, it is experiencing that non-drainable section is having accumulated water, which is, if it is not properly removed while light up and operation, it will also impact for the BTL. So we have stopped every BTL, and it should not be a stop of hydro. It should be that hydro is only when the delta T is within the 50 or less than 50. If it is 4 to 5 days or 6 days of shutdown, if the delta T of hydro water and the metal temperature is within the 50, then we can have a hydro. We don't go for without this. But in the short time of 48 or 60 hours, we are not in a position to cool down header temperature up to certain range, so that we have stopped the hydro. Oxygen is 3.5. Instead of 3.5, we have started maintaining 3.1. The mill fineness, we have started isokinetic sampling, and based on that, rectification of orifice we have planned, and in the opportunity we have replaced a few orifice as the flow is unbalanced in that particular region. pH is being means water chemistry parameter. SCAP, we have a practice of SCAP in service, not in auto. We have a SCAP available, but it is not in auto. After recommendation, we have put in all auto with the operation condition. Ash flow, eco hopper, these all some measures we have started. And thank you. Does anyone have any questions? No, I am not saying that hydro test to be stopped. We have a practice of boiler hydro after BTL. But in the BTL, if we are not having the delta T less than or equal to 50 degree, then it is detrimental for other damage after this hydro test, because we are unnecessarily stressing hot means hot temperature with respect to normal water. It will lead some additional failures in the other zone.
Sir, do you try any cyclic type of hydrolysis?
We have not tried here, but cyclic hydro also, it will say that it should be within 50 to 60 degree of delta T. Then only we can have a process of cyclic hydro, at least 3 cycles of 100%, 70%, and 50%.
Ligament crack or due to this hydro test. So have you any photograph for this?
Right now it is not there. I'm just sharing afterwards. We have a ligament kind of failure, ligament cracking in the stub joints and other. But
who is asking? From where?
The JSW BPS question. JSW question.
Sure.
Yes.
So are you facing a problem of this ligament cracking, or why you need a cyclic hydro?
We are facing during hydro, we are facing some type of crack in the rear
other zones.
side water
Where
mass.
crack? Side water mass.
Sir, side water was around 50.
So do you have a practice of hydro after the every shutdown or every tube leakage?
No, we have practice for shutdown. We have practice for that hydro test. But right now I'm seeing there to avoid hydro for preventing ligament cracks. So I want
So when you are doing a hydro, are you seeing the header metal temperatures?
oh, yes, sir, we are seeing there
What are the header metal temperatures?
around 50. Yes.
50. You are seeing the metal temperature. I am talking of the header metal temperature.
Header metal temperature.
Yes, what you are saying is the tube metal temperature.
No.
But header metal temperatures are in the
That-
range
that
of
is-
300 degrees,
Yes,
250
sir,
degrees.
that is new for me. That's why I'm asking.
No problem.
Yeah.
I want to just discuss so that your all queries
We
can
are
be.
facing some types of cracks. So that's why I know which type of practice is here. So preventing.
Hydro, after every shutdown, you should measure the header metal temperature. If they come below 150 degrees centigrade, only then we should go for hydro.
That things I'm noting, sir.
What you are doing must be, you are seeing only the tube metal temperature.
Human.
Yes,
Tube
because
gets cooled, but header doesn't get cooled.
Yes. That is I'm noting. Thank you, sir.
yeah, initially we have the
Don't
same
worry,
practice.
I'm just trying to clarify further so that
Yes, yes.
you should not
The
have any
header-
doubt.
Header also we need to maintain.
Yes.
Yes, For hydro, it should be-
Install the thermocouples on the adders, all adders,
Yes.
penthouse.
Must be given in the stream temperature there. It actually is not measuring the secondary measuring the temperature of the ground. And it takes time, 5 to 7 days, depending on what kind of cooling you are using. Otherwise, it will lead to this kind of thing.
And attachment failure, the way you are saying, it is not going to serve your purpose of cycling. Cycling is generally recommended when there are the chemistry failures, and in that case only when you are having multiple leakages, just to point out all the leakages we are doing.
2 times we had done the hydro, and then again and again we were getting cracks over the. So that's why I'm thinking that issue can be related on this one.
Failure
That is,
details.
sir, that is
Yes.
very good. That header temperature need also to check. Yes, sir, yeah, basically.
Yeah. Thank you.
Thank you.
Cyclic hydro is mainly where we are having means major failures. After doing hydro, we can face further leakages, so that we have a cyclic process of hydro, so that particular we have done the hydro of as per design of 100% or 1.25%. We have reduced
Cyclic hydro is not a common activity. It is not as per design. We don't want to do a cyclic hydro. It is rather detrimental, but in some exceptional cases when there are some type of corrosion failures and immediately we are not able to take any measures, which are long-term measures, and we want to overrun our boiler. So we do a cyclic hydro, we increase the pressure to the level of hydro pressure, then we reduce the pressure. Then again we increase, again we reduce, we do 5 to 7 times.
Yeah.
That is cyclic.
means in this the total hydro is in minimum 3 to 4 cycle, in which we have raised the pressure up to 50%, then again down, then 70%, again down, then 100%, and again 50 to 60%, so that we are stressing boiler tubes to identify if any loose or weak points are there that should come in the hydro. Yeah, it is not a regular practice. It is can be once in a while, once in after successful completion of overhauling or long shutdown, or after reserve shutdown of 15, 20 or like this.
जैसे आपकी गाड़ी रोड में खराब हो गई, breakdown हो गया, तो you take some measures.
Yes.
It's like that only. But it should not be a practice. It should not be.
I will add to it. Actually, cyclic hydro is required where frequent failure is there. If suppose you have did the overall, and within a span of shorter time it is come BTL. Again, you have attended that one. Again, in the shorter time you have BTL. Now this frequent if BTL is coming, the shorter duration, then you have to go for the cyclic hydro. What it means that you are having some sort of a problem which is not attended in the single shutdown or single attending doing the BTL. So for cyclic, we are going for the pressure, rated pressure or to the working pressure. Once you are reduced to the normal, again 3 times you are doing this thing within a span of. So by doing this, you can going to find out the weakest point you are having, and by attending that, thereafter you can ensure that you are not going to get the further delay. But it's not recommended for the normalcy of the head. It is only specialized cases where you are facing the problem of frequent leakages after any sort of the overall or program operation of the unit.
Okay, thank you.
Thank you, sir. Thank you for your wonderful presentation. It was containing the detailing and analysis and visual presentation containing all information. And I hope that we are going in the right direction to mitigate these boiler tube failures under the direction of our executive director and senior officials. Thank you very much for your wonderful presentation, sir. Now the next session will be handled by Mr. Vinod Chaudhary, the ex-executive director of NTPC, and no need of introduction for him. He is a veteran in the field of boiler. He has put almost 40 years in as a boiler expert, and today he will be discussing the presentation on boiler, and he will simplify the problems of boiler tube leakage. I welcome, on behalf of you, I take pleasure in welcoming Mr. Vinod Chaudhary, ex-executive director NTPC, to present the presentation.
Good noon, all of you. I'm going to discuss on strategy for zero forced outage. And this strategy applies to all equipment. It's not only to boiler. It applies to all equipment of a power plant. I'll just read out second para of this synopsis. Power plants are generally operated and maintained in a conventional way. First of all, we allow damages to take place. And when these damages go unnoticed and result into breakdowns, we put a lot of effort and money to restore the equipment. Further breakdowns lead to substantial consequential damages, which increase both the loss of revenue owing to increase in downtime as well as increase in maintenance expenditure. So conventionally, this is what we are doing. We allow the damages to take place. Normally it goes unnoticed. And when failure takes place because of such damages, then we spend a lot of money, time, effort to restore the equipment back. So this is the conventional way of operating and maintaining a power plant. Okay. Now, what is the strategy for forced outage? All damages take place because of certain deviation in the process. And when we fail to identify those deviations, then damage gets initiated. So all damages are because of certain deviation in the process. And when we don't capture those deviations and we don't rectify those deviations, then damage initiates. And when that damage identification also goes unnoticed, see, no damage is abrupt. All damages take time. Then it continues. And then it reaches a stage where failure takes place. And when failure takes place, then our attention is drawn. In most of the cases, we don't do even root cause analysis. We don't try to find out the root cause of the failure. Because our whole attention is on bringing the equipment back, on bringing the unit back, because generation suffers. There is a commercial loss. So we want to bring the unit back as quickly as possible. So what should be our strategy? Identification, elimination of process deviation to prevent initiation of all damages. It should be our first strategy. We must identify all the processes which are causing the damages. And what is next step? Obviously, when I say that we should capture deviation in all the processes, we will succeed in capturing some, and still some will be left. So when some deviations are left, what those deviations are doing? They are causing damages. So when damages take place, then we have to capture such damages. So identification and capturing of all the damages. And when we capture damages, we also capture damage mechanism, because it is due to some mechanism that damage is happening. So both damage as well as damage mechanism have to be captured. But again, we will succeed in capturing some of the damages, whereas some will still get left out. So when some get left out, then that will result into failure. So when failure takes place, then we have to do the root cause analysis, because we have to find out the cause of the failure. And then once we have found out the cause of the failure, then we have to eliminate that cause. Because unless you eliminate the cause will persist, damage will reoccur, failure will reoccur. Normally, some of the damages you can eliminate during the failure itself. Some of the damage mechanism also you can eliminate during the failure itself, but some will take longer time. Some may need some resources also, and you have to plan those things, and possibly elimination of damage mechanism can be done mostly during overhaul. Reduction of volume of work. I visited many plants, and it is true in NTPC also. We are doing a lot of work during overhaul. The quantum of work which we are doing during overhaul is very high. As long as we continue to do high volume of work, our problem will not cease. So if we want to eliminate the problem, you have to reduce the volume of work. You have to do less work. Then optimization of preventive. Even in preventive maintenance, we are doing excessive work. So a lot of study will have to be carried out to optimize the frequency of preventive maintenance. So overdoing preventive maintenance also is not good for the plant. Next. ये क्या कुछ काम नहीं कर रहा है क्या? So when you remember that we discussed about identifying the process deviation. Boiler water chemistry is one such process. A lot of effort should go into water chemistry, and every year or every 6 months, some kind of audit should be done to identify the deviation in the process of boiler water chemistry. And wherever you find there is a deviation, it should be set right. It should be corrected. This is one area where maximum attention should be given. Power plant operation is another area. You will be surprised to know that many practices which we have adopted have detrimental effect on the life of the boiler components, and therefore those practices should be reviewed. Operation is not a subject. All of us must understand. I hope some people from operation are also here. Operation is not a subject. Boiler is a subject, but operation is not a subject. Turbine is a subject. All equipments are subject. And therefore, how the equipment should be operated should be given by the person who understands equipment, and not by the people who have been operating the plant for 20 years. No. All procedures for operation of an equipment should be given by the person who understands about the equipment, understands the design of the equipment, understands the manufacturing of the equipment, erection and commissioning of the equipment, commissioning of the equipment. People who understand all these things should only give the procedure for operation of the equipment, and our operation people should simply stick to those procedures. They should not deviate from that, because every procedure which is given is with respect to the design. Every design has a limitation. So procedures are drawn from the limitations which are there in the design. So please understand that same equipment by a different designer, by a different manufacturer, can be operated differently. It may not have the same operation procedure, because depending upon the limitation of the design, he will set the procedure for operation of the equipment. Combustion is a topic in itself. And if somebody doesn't understand combustion, then he will not do justice to boiler. The boiler can be maintained. Life of the boiler can be retained only if one understands combustion and one allows combustion to take place as per the philosophy. So combustion is another very important aspect which has to be kept into mind. The airflow balancing through PF pipes. This will have very large effect on combustion. So we have to take care of this aspect. Cold flow balancing through PF pipes. Then flue gas flow balancing through ESP. So I have listed out some. There are many more. So these are some of the processes on which we have to pay attention. And any deviation in such processes have to be identified and set right. Now, maintenance on an equipment should be done on the basis of condition assessment. In more than 99% utilities, we are doing maintenance of an equipment based upon our some kind of experience which we are exposed to while maintaining the equipment. But nobody knows how to assess the condition of the equipment and how to do work as per the assessment. I told you that excessive maintenance is also bad for the equipment. Just as inadequate maintenance is bad, excessive maintenance is also bad. So you have to understand the condition of the equipment correctly and plan your work as per that. So in such cases, condition of every equipment needs to be assessed so that any deterioration, defect, deficiency in the equipment is captured and eliminated much before the stage of failure is reached. All damages and damage mechanisms are captured during equipment condition assessment. Now, this is the third stage. I told you that first step is capturing the deviation in the process. Second step is, if we fail to capture the deviation, then we have to capture the damage. And third stage is, if we fail to capture the damage, then obviously the failure will take place. And in that case, root cause of the failure has to be found out. So this is the third step. Now, when we talk of BTL, we cannot talk of BTL without talking of overhaul. Because in power plant, especially in boiler, very few equipment have redundancy. So most of the equipment do not have redundancy. Obviously, pressure parts do not have redundancy. So equipment, why overhaul is done? Overhaul is done because for equipment which do not have redundancy. Otherwise, there is a concept called preventive maintenance. So preventive, for all equipment which have redundancy, we are doing preventive maintenance. But the equipment which do not have redundancy, we have overhaul. Overhaul is the only mechanism by which we can maintain the health of the equipment so that we get reliable operation throughout. And there are two words which I have written: complete and effective. So overhaul has to be complete. Now, during overhaul, we do some work. You can call it overhaul, but that is not the complete overhaul. Complete overhaul is when we have identified defects of all the equipment and we have taken the corrective action. That is called complete. And when we say effective, that means execution should be such that it doesn't cause any secondary damage to the equipment. So we should be able to restore the equipment to its original state, just as it is a new equipment. Just because you can expect a reliable operation from a new equipment. But when some deterioration has taken place in the equipment, then not only reliability gets affected, performance also gets affected. But when we restore the equipment back to its original condition, to its new condition, then we say overhaul is effective. So overhaul has to be both complete as well as effective. And what are the things required? Most important thing is preparation of comprehensive scope of work. This is the most important thing. So if you don't prepare the comprehensive scope of work, then going for overhaul will not give the desired result. And what are the bases? Condition assessment is the most important basis for preparing the scope of work. Only during condition assessment, you will come to know the condition of the equipment and the necessity of doing some work during overhaul. Then equipment performance assessment. It is not only from the reliability point of view that we do the overhaul, we also have to restore the performance of the equipment, because as the equipment runs, there is deterioration in the performance. So during overhaul, you have to restore the performance of the equipment back. If the boiler is old, then you have to carry out residual life assessment. And recommendation of the residual life assessment will also form part of the scope of work. The root cause analysis. I told you that all the failures which have taken place, we must do the root cause analysis, and recommendation of the root cause analysis also should form part of the scope of work. And then, of course, we have history of defects generated by our operation department, maintained by our MTP, and that should be taken into the scope of work for overhaul. And of course, other things are elementary, identification of spares. Now, it is elementary, no doubt, but it's very important. Our requirement of spares should come from scope of work. Whatever we have decided to do during overhaul, our requirement of spares, unless we have spares, our overhaul will not be effective. Then timely procurement. It is not enough that we have moved the indent. Procurement should also be done timely. Then for contract services also, all contract services should be tied up well in advance. Normally, we are doing it just 1 week or 10 days before the overhaul starts. That's not enough. See, just as you need time for planning, everybody needs, all your service providers, they also need time for planning. Normally, the quality of work suffers because we don't give adequate time to our service providers. And then execution of work. Now, when we monitor execution of work, we have to monitor from the point of view of quality and also completeness. Whatever we have decided. Now, normally what happens? We are slow in the beginning. There is pressure from the management. And all the work which we have envisaged, we don't execute at the end because time is lost and management is not ready to give extra time. Then we box up the boiler with incomplete work. So completeness with required quality within overhaul period with utmost, and safety is of course another important factor. So any work which is done, it has to be done safely so that there is no even minor accident. Now, why maintenance is required? Actually, maintenance should not be required at all. But maintenance is required because in some of the boilers, you will find there is design deficiency. There are manufacturing defects. There are defects introduced during erection also. Commissioning defect. Then there are process deviations. Those process deviations are causing the damage. Maintenance-induced defect is the most pronounced reason for necessity to carry out maintenance. You will be surprised that 50% of the maintenance requirement is because of maintenance-induced defects. And that is because we don't have any procedure for carrying out the maintenance work. We don't have. And the agencies whom we hire, the kind of people we hire for carrying out the work, they are also not trained. Anybody and everybody comes and starts doing the work. And this is single most important factor for increasing the maintenance required. Combustion deviation is, of course, and there are other damage mechanisms which generate the requirement of maintenance. What is the scope of condition assessment? So we have to identify all those design deficiencies wherever it is there. Identifying manufacturing defect, identifying erection defect, identifying commissioning defect. See, when you say commissioning defect, a lot of set points which have been given in the beginning. Commissioning team puts some set point and they make it operational. Well, later on, when the plant is operated, you come to know this set point is not correct. So they have to be changed. Identification of all damages and damage mechanisms. This is very important. And root cause of failure is, of course, if we fail to arrest the deviation in the process, if we fail to arrest the damages which have occurred, then it results into failure, in which case we have to do the root cause analysis to find out why the failure has occurred. And then identification of process deviation, because all damages are because of some deviation in the process. So looking at the damage, you have to find out where deviation in the process has occurred. These have been a list of performance assessment equipment of for performance assessment. And like all these tests have to be done. They have to be done regularly. And if we do the tests, then you come to know the performance of the equipment. And based upon the performance, deterioration in the performance of the equipment, you can take certain corrective action during overhaul to restore the performance. That is also our job. So reliability is not the only job. The residual life assessment. If the boiler has been operated for 1 lakh hour, then we must go for residual life assessment. Of course, boiler has a much more life than 1 lakh hour. But at least after 1 lakh hour, we must go for residual life assessment. And some of the components which have a much longer life, the life of such component should be assessed to understand that it has got so much of life left and we need not worry much about it. Because depending upon this residual life assessment, we will decide the frequency of life assessment that is required to be done. So residual life assessment to be repeated depending upon the report of first residual life assessment. So first residual life assessment will be doing after 1 lakh hour, but depending upon the report of this assessment, we will decide the frequency of repeating the life assessment. When we talk about execution of work with required quality, finalizing methodology of work. It's a very important thing. People are doing whatever way they like. And in most of the cases, you will find that doing work is harmful, more harmful than not doing work. Again, I'll tell you, this is because we only see the name. It is this agency which has done some work. But let me tell you, it is not the company which does the work. It is the manpower which they bring along with them, which carry out the work. So it is not the company. Company may be good, but if the company has not brought the required manpower, the skilled manpower, then it's of no use. I have seen that same company performing well in a plant, but not performing well in other plants. That is simply because the plant in which they are able to get good manpower, they are able to perform better. The plant in which they fail to bring good manpower, they don't perform as per the requirement. So, methodology of work has to be given by us. How a work has to be carried out, that complete methodology should be given by us. And if we don't give, then they will try to do whatever way they can do. And mostly, money is the criterion for them to decide the methodology of the work. A methodology which will cost them more, they will not prefer to adopt that. They will normally try to make a shortcut. And in most of the cases, every overhaul makes a boiler worse than what it was earlier. Every overhaul. And that is why, as time passes, our volume of work goes on increasing. It doesn't come down. And how we justify this? We justify this by saying, sir, equipment has grown older. Sir, boiler has grown older. Sir, boiler has been operated for 1.5 lakh hours of operation. Please try to understand. If we are overhauling a boiler in 2 years, we call it an overhaul only when we restore the boiler to its original condition. So every two years we restore the boiler to its original condition, then how do we say it has grown older? If we don't do overhaul for 20 years, then we can say, yes, it has grown older by 20 years. But when we are doing overhaul every 2 years, then we are supposed to bring the boiler back to its original condition after the overhaul. So it is as good as new. And when it is as good as new, how do we say it has grown older? And why do we say the volume of work will increase because it has grown older? No. Its volume of work increases because we don't adopt the right methodology. We damage by doing work. So, methodology of work is very important for execution. Completeness of work. Again, I'll tell you that we start the overhaul with some volume of work, but when the required time is not available, then we wind up and short close. So completeness of work is another important thing. Quality of work. If we cannot do a work with required quality, it is better not to do the work. Unless we ensure the required quality, we should not start the work. And of course, safe working it goes without saying that whatever work we do safely, so that there is not even a small injury. How to reduce or eliminate breakdown? Again, correction of process deviation. So, wherever deviation in process has come to our notice, we must do the necessary correction. If we don't do the necessary correction, then such deviation in process will continue, damages will continue, failure will continue. So starting point is process deviation. Elimination of damage and damage mechanism. So it is not enough that we replace the tube. We should also understand why that tube has got damaged and what has gone into it. That should be identified and necessary correction should be done. If the flue gas velocity is high at certain corner, certain location, and that is causing the damage of the tube, then we have to correct that. That high velocity point has to be corrected. It is only then damages can be discontinued and failure can be discontinued. Root cause analysis. Again, if a failure has taken place, then we must find out the root cause of the failure. And only after the root cause of the failure has been ascertained, we should take the necessary corrective action to eliminate this. During breakdown maintenance, we don't care about the quality. That is because time is short, scaffolding is scarce, temperature is high, space is small, many people cannot go and do the work. So somehow we do the repair and come out. But later on, during overhaul, we don't restore it to the normal condition. We forget. All failures which have taken place and whatever repair work we have done, we know that we don't do as per requirement. But necessary correction must be done during overhaul to restore its normal condition. And it goes without saying that in every activity that we undertake, safety has to be an important part. Preventive maintenance also needs to be optimized. So we should study the behavior of the equipment and try to understand the requirement of preventive maintenance. So it is not necessary that if we have decided that every week we have to do the preventive maintenance on an equipment, we should continue with this. We should study the behavior, whether it is required every week or not. Can we increase it to fortnightly or a monthly or bi-monthly, like that? And during preventive maintenance also, if we come across any damage in the equipment, then we must understand the damage mechanism and try to eliminate both the damage mechanism as well as the damage. There is a small slide, but very important. How to make power plant accident free. I think it is important for you also. So it's not only that we work on the reliability of the equipment, we should also work on safety aspect. And here again, I'll tell you, there is no SOP for the maintenance work which we carry out in the plant. And depending upon the agency that we engage, they are adopting different procedures for doing the work. And mostly you'll find that safety doesn't figure as an important aspect in that procedure. So for every maintenance activity, required SOP should be made, keeping safety into mind. Deployment of skilled manpower. This is another very important. Anybody and everybody, we hire and put them into the job. That will not work. Only skilled people, people who are familiar, people who have the experience, people who have the knowledge should be engaged. So if you put anybody and everybody, then there is a greater tendency for accident to take place. We should not carry out the work without assessing the safety conditions. And if there is any unsafe condition prevailing, immediately it should be corrected and work should not be started. So before starting the work, unsafe condition must be assessed, and if there is any, should be eliminated. There should be strict compliance of SOP. If the SOP is not followed, so it is not enough that we make SOP, we should also make sure that SOP is followed both in letter and spirit. And then there should be supervision of work from the safety point of view. See, when you supervise a work from the completion point of view, from a point of view that it is completed early, then our focus is different. But when we supervise from the safety point of view, our focus changes. So a person who is supervising from completion point of view will be different from the person who supervises from the safety point of view, because the focus of both the persons will be different. So any work which is being executed should be supervised from the safety point of view. How to improve quality of work? Plan unit overhaul well in advance. Now again, this is very important. I told you that if you don't give time to your service provider to arrange good manpower, good workforce, then he will bring anybody and everybody. And once he brings bad workforce, any amount of supervision will not improve the quality of it. A person who doesn't know how to do, are you going to teach every step all the time, 24/7? No, it is not possible. So you have to give enough time to your service provider to engage good manpower. It is not that good manpower is not available, but I told you that they are all floating. So whoever engages them first, they go to them. If you are late in engaging them, then they are not available. So overhaul has to be planned in advance. Date, you have to adhere to the date. It is not that it is your wish. Anytime you will shut down the unit. If you shut down the unit anytime, then that manpower goes. Then whichever unit has been shut down, they will all be engaged in that unit. So you have to adhere to the date of the shutdown, and you have to award all contract sufficiently in advance. If you are awarding 1 week or 15 days before, where he will bring manpower from? Then whoever is available, all left out ones, they are brought. It doesn't work. Please understand. Please attract best agencies. I tell you, giving 5%, 10% extra to a better agency is far, far better than awarding the same contract at a price 5% or 10% or even 25% less and bringing a bad agency. It has multiplying effect, let me tell you. It makes you suffer for a long time. A bad agency doing a bad overhaul tortures you for a longer time. Then use of advanced tools. And best thing is that all the power plants should keep those tools. Please keep those tools, because if you ask them to bring, some will bring, some will not bring. Some will bring some will not bring others. So it is better that you keep with you and give them on chargeable base. If they don't bring, keep them on chargeable base. Supervision is very important. I'm telling you, if you don't supervise the work, if you think that sitting in your cabin, you can monitor the work, you can control the work, then you're wrong. You have to be available where work is going on. If it is inside boiler, you have to be inside boiler. If it is second pass, it has to be second pass. If it is in between, that narrow gap between the two coils, yes, you have to be in that narrow gap between the two coils. Because if you don't go inside the boiler, they will do anything and everything. And at the end, if it comes to your notice, you can't do anything because time is gone. And whatever strategy I have discussed about, what will be the benefits of those strategy? Elimination of fatal, non-fatal accidents, complete elimination of equipment forced outage, including BTA, reduction in maintenance requirement. Now, how maintenance requirement is reduced? It is reduced because you are attacking not only the damages, you are also attacking the damage mechanism. So once you attack the damage mechanism, then similar damages will not take place. See, our role as an engineer is not only to eliminate the damages. Our role is also to eliminate the damage mechanism so that similar damages do not recur. And automatically, reduction in expenditure, reduction in air preheater leakage. See, if we do a good job on air preheater, then your air preheater leakage will get reduced. Reduction in APC. Obviously, if the performance of the equipment improves, then for the same power consumption, your performance will get enhanced and therefore your APC will come down. Your boiler efficiency must improve after overhaul. If your boiler efficiency doesn't improve, that means you have not done a good overhaul. Your plant heat rate should also, if boiler efficiency improves, if turbine heat rate improves, automatically plant heat rate will improve. Your stack emission will come down because when the gas temperature reduces, and then you will be doing some work on ESP also, your stack emission will come down. And then by improving the reliability, This may be true, this may not be true for you, but this is true for all power plants which have PPA, because there you have a fixed cost recovery which is dependent upon the availability of the plant. So if the availability of the plant improves, your fixed cost recovery improves. Your variable cost recovery improves because improvement in heat rate. Your fuel cost consumption will reduce, will come down. Then, if you are able to assess the condition of an equipment exactly, then your volume of work will come down. The overwork which you are doing may not be required to be done, and therefore your volume of work will come down, and that will reduce the duration of the overhaul. Suppose if you are overhauling a unit in 25 days, maybe you are able to complete it in 20 days, and in subsequent overhaul, maybe in 15 days, 10 days also. So, unit has to be shut down every 2 years, may not be required. A time will come that your boiler will become so reliable that you may have to overhaul the boiler once in 4 years or once in 6 years. Reduction in manpower. In anticipation that we have to do a lot of work, we force the agencies to bring a lot of manpower. And of course, they will not bring it free of cost. It is at a cost. So if your volume of work reduces, then the manpower which is required for that overhaul will definitely come down. I was telling you that gap between two overhauls. So currently you are doing once in 2 years. Later on, a time will come when you may have to overhaul it once in 4 years. And maybe even more. And all these things will have an impact on reduction in O&M cost. And increase in profitability. So, in conclusion, I'll say, capturing process deviation and initiation of damages and damage mechanism much before the equipment reaches the state of failure, and elimination of the same will not only eliminate forced outage, but will reduce O&M expenditure of a power plant to a large extent. And I must tell you that it is very much possible that we eliminate forced outage completely between two overhauls, be it BTL or any other equipment outage. It is very much possible. All that is required is some amount of assessment of the condition of the equipment and carrying out the work exactly as per that. Yes, a plant can be completely free of not only BTL but other outages also for several years in continuation if we follow this practice. And if we follow this practice, not only our forced outage will become zero, our volume of work will come down, our O&M expenditure will come down, our profitability will go up. By doing more work, we are not only we are incurring more expenditure, we are spoiling the equipment more. We are increasing the requirement of the maintenance requirement of the equipment in the time to come. And it does more harm. It doesn't give any benefit. So it is very important to understand the maintenance requirement of an equipment and doing maintenance only as per that. If you do maintenance only as per requirement, not only you restore the equipment to its original condition, you make it more reliable, you make it outage free, and there is many more benefits which accrue out of that. So friends, it is not surprising, it is not astonishing to have a plant free of outages, free of breakdowns, and that too at a lower cost of expenditure. It is very much possible. And you just try it and you'll see the difference. Thank you.
Thank you very much for your enlightened presentation, sir. It was a thought-provoking session and laying strategy and setting benchmark for zeroing down these forced outages. It was an excellent presentation, giving insight and scope and significance of defect analysis, root cause analysis, and condition assessment and performance assessment of equipment. And finally, you also highlighted to do this work in most ethical and conscious way so that we can reduce the volume of work done by adopting these right methodologies. Thank you very much for your knowledgeable session, sir. And now the session is open for discussion. If you have any doubts, you can ask. Make it very short. Before lunch, we have one more session. So if you have any doubts, you can ask. So I think it was a very wonderful presentation, giving no room for any doubts. Sir has given very clear thoughts. Sir, I think everybody will take your learning and they will try to implement in due course of time. Thank you very much, sir. The next session will be handled by Mr. Umar Ali, L&T MHA boiler, who is having the specialization in welding technology, having more than 17 years of experience. The presentation will be covering introduction to critical material, challenges in dissimilar welding, and chief failure mechanisms with case studies. Now, on behalf of you, I invite Mr. Umar Ali to present his presentation.
Thank you, sir. Thank you for giving me opportunity for presenting today here. So please. So thank you. So along with me, Mr. Ashish Nagar from our team, he is also joining. He is also here. So So in today's presentation, I will try to cover our introduction, then material in the supercritical boiler, challenges in dissimilar welding, especially with Super 304 and is it 213 T92. Okay. Then reasons susceptible for to travel in coal fire boiler. Then basic tube failure and its mechanism and preventive measure. Some case studies also there. Then solution aligning and stress corrosion cracking. So actually, L&T MHI boiler is a joint venture between L&T and Mitsubishi Heavy Industry. So this joint venture is formed it around 2007, and till now we are in the same. So our head office is in the Faridabad and manufacturing in the Hajira and manufacturing Hajira for pressure part and pulverizer and other equipment are getting from different supplier entire from the world. Okay. So this is our capacity, 4,000 manufacturing capacity megawatt. Okay. Then we are into engineering, marketing, engineering, designing, procurement, manufacturing, logistic, installation, commissioning, after sales service, operation spheres, safety, and quality. So just I'm forwarding all this. This is our design capability. I'm not going into detail on this. This is the introductory slide actually. So this is our capability, design capability for Khadgaon project and Tanda project. Just I am showing here. This is our some product, critical product manufactured at Hajira shop. The header, panel, piping, and coil. So this is water separator drain, tank, then the burner panel, vent panel, furnace inlet manifold, rear wall upper panel module. These all equipment are in-house only. And then this is a superator coil assembly. This is fuel firing burner and wind box. And this is a 32 meter header for 1000 megawatt. This for I think Indonesia, we're exporting it into different countries also. So this is our capability for pulverizer mill. So this is our erection capability. We are all erecting complete power plant at the site. So this is the first ultra critical boiler of India, ultra super critical boiler of India. That is a Khadgaon NTPC Khadgaon project. Sir, I think Sir was also involved. Sudhir Sir was also involved in this project. Okay, this was proud of our country basically, and we finished it in the record time also. This is our footprint in India, and this is our global footprint. Why I'm just pulling it faster moving this slide. This is just for informative only. So this is a supercritical. There is a supercritical and subcritical technology. So there's a difference. Supercritical technology once through boiler, and subcritical is a recycling the water and all this things. So this is the efficiency wise. If subcritical boiler efficiency is up to 40%, in supercritical boiler it is 42%, and ultra supercritical it is up to 46%. And advanced ultra supercritical is also, we are working on that, but their efficiency can go up to 50%. This is one slide I want to do. So this is our achievement of hydro testing at site. If you see, we have started in 2010, and the first boiler hydro tested at around 2012, JP Nigri. On that, we have faced around 21 leakages in the boiler, in the stub joint. But thereafter, we have taken so much precaution and followed SOP and all these things. And after that, there is no leakage, if you see. And after Ghatampur also, we have recently, just last week only, we have completed hydro test of Buxar also 2660 megawatt, and THDC Khurja project at near Delhi only. There is also no leakage in the boiler. Just 10 days back we have completed. It is not added here. So here I have to cover only this few material also. This is critical material. So this is just a recommend our nomenclature of the boiler, what material, just for introduction. You know? And this is the material where we're using. For header, we're using up to 92. In the metal being used in pipe also up to 92. And in your panel, carbon steel up to 52. And in your coil, 3040, 92. All critical metal is there. This is again just reprinted. This is a material for P91, P92 we are using in the main steam pipe. In Khargaon, we have used the first time P92 material, and before that, people are using only up to 90 on grade. This is what I want to do. So see, if you are using a critical material, high alloy steel, then we can reduce the thickness of the pipe or any component. So this is actually steam condition trend of the pulverizer coal fire. So if you see here, we have started from subcritical boiler, maybe in the 1950. Then we moved to, we have increased the temperature and pressure depending on the requirement of the industries. And we have moved from subcritical to supercritical in around 1970, where steam temperature is around 566 and the pressure is 25 MPa. After that, now we are here. We have in this region where now we are in the ultra supercritical. First time we have given in this Khargaon project, then THDC Khurja, right now we are executing, and for Buxar project also we are executing ultra supercritical boiler. Here we are using 92 grade material as well as Super 304. That because the temperature is and pressure is very high. So here you can see the strength of material, creep rupture strength of the material. How if you increase the chromium percentage, then if you increase the chromium percentage, and you'll find the creep rupture strength is more. And if you creep rupture is more, it is required in your boiler, then you have to select the good quality material, right from T22, then 91, 92, and Super 304 up to Super 304. So higher creep strength is mainly due to alloy and microstructure. So, this is what I wanted to talk about. This is a Super 304 metal. This is a very, very important material in the boiler industry, for especially for ultra supercritical. Here we are using, this is actually as per SA 213, ESM ASA 213, and this material is using in a very high temperature and the critical zone, basically in the final superheater area. It is below roof and up to above roof, you can say, the furnace upper side. And this tube, actually, we are generally, I don't know what other manufacturer is doing, but we are using sword fin tube. Sword fin means inside you have to make giving some compressive strength by putting some extra blasting or something. The different technique is available in the market. Then that way we can increase the compressive strength of inside of the tube, and we are using this tube right from Khargaon, and this time also using. This is our requirement, design requirement, and in this way we are reducing the damages of the tube. If you see LMB boiler in different with different client, our BTL is less as compared to any other OEM. You can say this is, court case also. It is called Super 304 also. Yeah, yes, it is court case. What is it? I am talking about Super 304 only, sir. This is the composition of Super 304.
How material is known as?
Yeah. Yes, sir.
That's standard. This material is called Super 304.
Yes. So this is the micrograph of Super 304 is still in receipt condition.
Yeah.
And
Can you please go back to the previous slide. Yeah, so one slide back, please. Yeah, so here you are saying that copper, niobium, and nitrogen are the special features which are typically added to this Super 304 range.
yes,
So can you please explain what is the role of copper, niobium, and nitrogen? Copper, niobium, and nitrogen.
it is added the advantage of your stress corrosion cracking. And this is T92. This is a micrograph of T92. Here microstructure requirement is tempered modern site. Okay, and heat treatment is normal and tempered condition. So this then this is the additional requirement for 92 grade metal. This is very important. This is that is product analysis and transfer tension test. This is the what supplementary requirement given in SS 335. For all these supplementary requirement we are using. This is the most important is your you see the delta freight, and then chrome nickel percentage. So all these things we are following in this in case of our boiler. Simulation heat treatment also we are doing for 92 grade. So this is the property at a high temperature. This is the what I wanted to show you. This is the steam side, and this is your furnace side. Okay, this is so inside the steam pressure, this is a creep exposure, and outside is your fire side, the condensate metal, surface gas, there's a flow gas. All these things are coming. Okay. This is creep rupture strength. How it is stress is decreasing as the temperature is increasing. Okay. So the creep rupture strength of 92 tube basically this is. So if during time of rupture, how it is temperature is, this is given actually. This is the effect of different alloying element here. If the creep strength is affected by content of chromium, nickel, vanadium, tungsten, boron, as well as by nitrogen and nitrogen aluminum ratio. here you can see the different element and how it is increase the property of 92 grade. So this is very important. So here I need to actually just this study may be different of a different design of the boiler, but as per our assessment, LMB assessment, your failure of is by erosion 35%, fatigue 33%, and creep 20%, and other 6% and 6%. Okay. So this is as per our assessment of LMB design boiler. It may be different for different OEM. And failure area of pressure part damages is a small piping, then piping, header, and all these things it is given here. Okay. So this is detail. I'm trying to cover in the detail where damage is coming, in which area the boiler damage is. This is because of acid erosion, because this is nearby your wind box and all these things. Then furnace oil tube is erosion around the slag area. The creep damage is this is the final superheated area. This is the chances of creep damage is more. Then in the nose area, your erosion is coming. Okay. Then here cracks in the weld toe, it is coming. This is the corner area. Then erosion by soot blower, because of this is again by erosion. That this is a high temperature condition, this area. So, and this is the ash erosion damaged by pollen. So I tried to cover the where damage is coming more and in which area. Okay. So in the dissimilar welding, there is a challenges in dissimilar welding. Actually, in this highlighted area, red area, we are using stainless steel. This is Super 304 tube. This is the upper side of the furnace. Then we are facing few challenges for development of this welding. Earlier, generally, we used to take this welding from MHI Japan, but since last 10 years, we have developed this welding at our shop Hajira. So what are the challenge you have faced? Is the thermal expansion difference between two variety of the steel. The thermal expansion is stainless steel and T92 is very different. Okay. Then carbon migration from heat affected zone of alloy steel into the welded metal. Okay. Then having a stable microstructure, we have to make the stable microstructure for T92. Eliminating hot crack at crater and controlling the inner post pass temperature, at pass temperature. Then controlling the PWST and stress corrosion cracking. So this way, how the thermal expansion, how we are managing by using NiCr3. This is inconel wire we are using for welding between stainless steel, that is Super 304 to T92 tube. So by using this, we can control the thermal expansion difference. If you see, this is Super 304, this is the thermal expansion of Super 304 this, and T92 is this, and the filler wire thermal expansion is this. If we welding with this, then we can make in this. We'll reduce something 304 to here and this, so we can compensate. Then carbon migration from heat affected zone of alloy steel into the weld metal. So again, here also, if we use this wire, that is NiCr3, this is inconel wire, then we can compensate this one. They are having a stable microstructure. So if you see this is the T92 side, or this is 304 side. Okay. This is a welding. And if you see, we have a balance by using inconel wire, we have balanced the hardness of different area. Okay. by this is T92 side, this is 304 side. Okay. So again, eliminating hot cracks and crater cracks. Actually, this is not coming easily. We have this is the hit and trial method. We have welded many times using different parameters. Then we have established this procedure at the saw. So finally, we achieved the welding without a crack. This is some welding process. We have to keep the torch somewhere and then pillar wire. This is again the hit and trial method. Nothing is given in the any theory and in this book. This is controlling the sensitization. How we are controlling the sensitization during PWST, we are protecting the job by protecting a plate and something. This is the development method of the welding. So I'm not going into detail. This is how we qualified the WPS and all this thing. We have a WPS for 304 to 92, 91, 32, and 12 also. This is some programming. This is since we are using this automatic welding, we have a different program for welding. So this is how we are doing welding of Super 304 to T92. This is automatic TIG welding. This is the quality control measure. What we are doing all this quality control measure, right from RT, VT, and all these things. So then IGC test we are also we are conducting. IGC practice E we are following here. Then the mechanical testing. This is the microstructure what we are getting after welding. Okay, this is the 304 side, and this is 92 side. This is your weld metal, coarse grain, fine grain, and integral corrosion, and the base metal. So what do we record and what we are getting? This is the microstructure we're getting in the after welding. So our weld joint is successful. So stainless steel material is basically Super 304 material is very critical in if you are doing bending up to some bending ratio and all those things. So if you are doing bending, then solution heat treatment is required as per the ASME code. So what I am just telling you here, because this is the failure we are facing in this because of yeah, first I'll discuss this slide, then I'll reverse on that slide. So this you see, as per code, if you are using Super 304 metal, then if forming is exceeding 10%, then only you have to do the solution aligning of the tube. But what we are following this one in 15%. Sorry, as per code in the 10%, 15% be karna hai, but we are following in the 10%. So we are using most stringent criteria for solution aligning. So that is one of the reason we are not facing a problem in the Super 304 tube at our boiler. So this is one of the biggest reason. And second reason, what I told, that is we're using short pin tube. So this what I wanted to discuss. This is those people are using Super 304. Maybe they are facing stress corrosion cracking at their site. So how it is actually developed, this stress corrosion cracking? You see, this is the three things. Three parameter is if combined together, then stress corrosion cracking will come. This is susceptible material. Maybe it is sensitized because of high temperature, or then the stress, tensile stress. Then corrosive environment, it may come from water, sea water, or rainwater from anywhere. Then stress corrosion cracking will occur. This is a technology of stress corrosion, how it is coming. Yes, sir.
Sir, 1 minute. Sir, Hello,
Yeah, tell me, sir.
sir, Mallikarjun, Jindal Power, Simapuri Power Plant. This 304, before welding, post welding, preheating is also be must and should be required, no?
Yeah,
As a,
post preheating, post weld, or post heating, then PWST.
is
Before
must and required.
PWST, you have to come down the welding also up to less than 90 degree. All these things you have to do. I'm not going on all these things in the detail. If you ask, I can discuss on that also.
As the same as a P91, P92.
Yeah.
Like processor is
Whatever
required.
you are telling, it is absolutely right. It is a mandatory requirement. So I'm not going on the detail because of time is the limitation.
Okay, sir. Thank you.
You are telling something, sir? Yes, sir.
He's telling about super 304.
Yeah.
Both are different.
About a lot of.
Another factor is tensile stress. And third factor is the material itself. There are certain materials making the material resistant to.
Yeah, somebody was asking, sir.
Third factor is susceptibility of the if you become less susceptible, if the more susceptible.
Thank you, sir. Thank you. This is what I need to show how this is a green. Somebody. So you see, this is a grain boundary. Okay, and this area, the stress, tensile stress is there in any place in the tube. Then this is the chromium rich zone. Okay, and grain boundary attack. This so chloride content in the grain boundary attack. This carbide precipitation is basically phenomena that you may knowing. So by this way, this area will have a less chromium. So attack will be start from this area. This is the grain boundary area. This is very. So that I need to show this how it is happening. Okay. So this already we have discussed. For solution leveling, we are following a stringent requirement. So this is our solution leveling parameter. How we are doing solution leveling in the soft flow. Okay. 1110 to 130 degrees centigrade heating, then we're cooling in the air or other method. So I'm not going detail in this presentation also. This is what we're testing after solution during solution during qualification of the solution aligning. This the check method basically. So again, we're doing performing solution aligning since 2014. Earlier, we were taking from MHI Japan. Okay, until that we have not received any failure because of solution aligning. There's some failure mechanism. This is the creep failure. This is because of fatigue failure. Okay, and this is corrosion, and this is where an erosion. I'll come by one in the detail. This is there are two type of creep. One is a short-term creep and this is a long-term creep. Okay. In the failure of metal due to rapid increase of metal temperature in relatively short period is defined as short-term creep. Okay. So like sometimes some temperature is increasing suddenly, then short-term creep may be occur. So this is for the long-term creep, some example of the long-term creep. This may be some larger and then the size, but it is comes in the during long service. Okay. Then this is the technique of how creep rupture is happening. Okay. Flagging, maybe something is there, maybe for material or something, then overheating, then creep. Okay. So this is the mechanism of creep. Okay. So because of time constraint, I'm skipping some slide. Okay. This is another example how creep mechanism coming. This is operation time, then stage of constant creep, then stage of accelerating creep, thoda dheere dheere bada, then it is rupture. This is another example. I'm not going into detail. Okay. This is fatigue. There are two types of fatigue. One is mechanical fatigue, and another one is your thermal fatigue. So both the fatigue you can find out in the boiler tube, because this is an example of few thermal fatigue. This is some a few example of the creep fatigue. One type of fatigue is there, that is a corrosion fatigue also. This is the mechanism of fatigue failure, thermal fatigue failure. You see, this is the spacer, and generally fatigue failure is coming in this area of the tube. I mean, attachment or something is there in the pin. This is the area very prone to the fatigue failure. Okay. This is again thermal fatigue failure. In this area is very prone to the thermal fatigue failure. So I'm moving faster to show some real example because of the time constraint. So this stress corrosion cracking I've already discussed. This is something what we see, the crack in the attachment is because of crack due to thermal expansion difference between the scale and base material. The ash scale is attached, and the thermal expansion of ash scale is something, and tube is difference. So because of this difference, your crack is there. I'm going to. This is erosion very, we will already discussed in the first slide. So this is a very common problem in the boiler tube. How erosion is coming, you see this is because of gas flow or ash flow. Erosion is tube erosion is occurred. Okay, this is the one formula is also there. How tube erosion is occurred and how much it is occurred if you're depend on the operation or density of the ash, speed of the gas flow. So how thickness is reduced, you can calculate also if you have a operation hour, speed of the gas flow, and density of the ash, then you can calculate the thickness reduction. So protector plate, I think you are also using in your boiler to avoid the ash erosion. This is the protector plate way of fishing. Also. This is the one just to identify what type of failure is there. So to identify or confirm what type of failure is there, this type of check is preferred in our boiler. This is the M is the main checkpoint, and C the checkpoint depend on the situation. So for creep, we have to see the appearance, inside condition, dimension, cross-sectional microstructure, inner side property, fractography, hardness, then MTRT, then precipitate distance method. Like similarly for creep, mechanical fatigue and corrosion fatigue, we have to check or reconfirm what type of issue is there in your boiler. So I'm just showing few site failure experienced by us. This is the one of the problem. This was the basically stub joint between the your drain pipe during hydro test. Yes. There is electron microscope you have seen, no? Yeah. With the microscope testing, basically for a particular area, you can see the chemical composition. In general spectrography, what we got, you will get the chemical composition only for the whole material. But if you want to see the microstructure of grain boundary or at a little distance, because microstructure is not same everywhere. It is a different in the micro level. So that test will help you to get. Okay. Yeah, tell me, sir. You can add, okay? Yes.
Yes.
It is actually used to determine the chemical composition
Hmm.
along a particular area. For example, you
Yes.
designate one particular area of interest and you want to know what is the concentration of various elements present in that area. Number one. Number two is if you want to see the gradient along a particular line. Okay. So EPMA will help you give you the gradient of chemical composition along a particular line. That's what that's here.
Oh, thank you, sir. Thank you. Thank you.
I guess in this connection, you were showing that chromium distribution of the brain. So EPMA probably will allow you to map the availability of chromium all over the brain and identify where the chromium reduction has happened and the weakening is. Right?
No, you cannot. You cannot. So what we are discussing here, this during hydro testing, this valve actually, this is a drain pipe failure because the valve was come out from the joint and it is going to somewhere else, maybe 20 meters further, and there is no accident, but this is the failure of your socket weld joint. This is, and then we have investigated why it has failed during hydro test. Okay. So during investigation, we have done so many all the method. Then finally, there are two possibilities there. One was a brittle failure that cracked center line of the weld, originated from the crater of the weld, and second was the improper PWST. So these are the two chances are there. Then we have further studied their hardness and all these things. Checked microstructure we have checked, and the direction of the crack also we have checked if anything is there. Then finally I'm coming to the conclusion. The hardness test data what shows that was 380 then 370. If the for 91 grade hardness value of this is very high. Normally it is coming if you are not conducting the PWST. So this metal is supplied by some vendor, and finally we find out after this hardness value, we gone to their supplier works also, and there is just some issue in their record also. So it was confirmed that they have not performed PWST. So this is the root cause. So So to avoid this one, what we have done in the site, there are similar joint was there at the site. There is around 280 joint. We have done 100% hardness checks at site. So to confirm whether they have not done PWST in other similar joint also. So we find the hardness was, in some joint we have find out hardness was more, then we have done PWST at site also to avoid this problem again. And after that, we have not faced any problem till date. Sorry, there are 1121 number of joint was there, not 280. And after that, we have done PWST of 280 joints again. This is one failure, that is a tube failure at the site. This you see, this is the first connecting tube of outlet header. The tube was failed in the bend area. So after study microstructure and hardness, what we find out here, due to the partial blockage by fault material, oxide scale slag etc. somewhere X lower bend in the loop. So if suppose some fault material, it may be during erection some paper. Sometime what welder is doing, they are, instead of putting the purging paper in funnel form, they are putting just ball ke jaisa bana ke dal diya andar. So this may be the one of the reason what we find out. So because of that, heat was accumulated in in the particular area, and steam flow was less. So because of this reason, this is the one interesting example. I don't know any other manufacturer has faced this problem or not. This is actually during a PWST of this fillet joint. Actually, in both the side, a valve was there, and we are conducting PWST of this welding joint, and it was blasted like bomb. No, in the site at night time, PWST is going on. It was blasted like a bomb. Unfortunately, I was also there on the site on that day. So nobody know how it is coming. This is PWST, how tube is filled. Then I checked the valve, whether valve is open or closed. I checked that both the valves was closed in fully condition. So I think because of during PWST at high temperature, the inside gas pressure and temperature is more, then it is blasted. What we predicted. This is my observation. It may be different. IIT people are also there. They can also tell something. They can add. But this is my opinion, observation, because I was there in the site. So this is my opinion. So there. But after that, other PWST have performed by opening the valve, but the same problem was not there. This is a failure of panel erosion near the wind box. This is also we have faced at the site. After that, we have placed additional protecting on that area. This is some case study of creep. If you see, this is the picture itself is self-explanatory. Okay. This is a mechanism of fatigue. This is a corrosion failure. So that's from my side. So thank you.
Thank you very much, sir. And now the session is open for discussion. If you have any queries, you can ask.
347 is a standard material. This is not a uncommon material. Okay. Anything else, sir? Which electrode? Electrodes are ER-NiCr3. This is also called in-cornel electrode. Okay. Yeah, ER-NiCr-3. Okay. Welcome, sir. Yes, yes. Yes, sir. Yes. Yes, sir.
I'm asking when we are going to be stand our materials so that we don't have any such type of failure, any type of failure.
Sir, very difficult question, sir. We cannot prevent the failure, but definitely we can reduce the failure. And in our case, it is very. I can.
But that's great. But we are fixing the problem.
Sir, this is my next question actually, sir. Next thing.
But my question is not that, sir. My question is when manufacturer guarantee that this boiler is not going to be leakage, whatever you do anything.
No, nobody can do. Actually, sir, most of the tube is failure because of. Nobody can, sir. No, sir. Actually, lot of parameter is there for the failure of the tube. Not only the material and welding. Okay, this is the lot of operation issues also there. Whatever the failure we have, what of the failure, just a minute, sir. Whatever the failure we have faced in.
Always there.
Yes, yes.
But my question when you are comparing the manufacturer, by what time you or anybody else in the world is going to introduce some sort of the material which is giving the sort of the guarantee that it's not going to fail, whatever with the condition.
I cannot, sir. I cannot.
Development of for the development of material. It is the development of material is not to prevent the failures, because failures are not due to the materials. Failures are our practices. If we are not running our boilers, our system well, that's the failures are taking place. The material development, for example, 304H, when they have used the 340H, then they have reduced the thickness and the weight of the material is less.
Yes.
Development of material is basically so that we can increase the pressure and temperature, because your sink is common. Your condenser pressure temperature is constant. You can't change that. But if you increase the pressure and temperature, then your efficiency will increase. That is the reason that efficiency has gone up to say 43, 46%. Yes, earlier it was around 30, 39% in the subcritical boilers. So the boiler is designed the way it should be run. That is the basic criteria, if I'm correct.
Yeah, thank you, sir. Sir, also want to add something. Actually, this is also some up to some extent it is possible. If you use the high grade metal, then cost it will not commercial utilization of that. It may be.
Today's scenario it might not be, but nobody knows the future.
Yeah, future nobody know, but I'm talking about the today's scenario. I'm talking about in the
very optimistic.
Yes.
Very optimistic.
And why we certain that one day it will come and where to get the material that also. But it's not by today.
Because if you are instead of 22, if you are using 91 grade or 92 grade or SS maybe, then the cost will go very high.
It is thought that we are having the mobile in our hand.
Yes,
And
yes.
we can call anywhere, but
Yes.
making the cost economic sense at that time. But nowadays you can say even a cycle person roaming in that cycle having the mobile phone, smartphone in the pocket. It that's the disruptive question. It might.
Yeah, we are hope for the best, sir. Definitely one day will come. There will be no failure in the boiler, sir.
Thank you, sir.
Definitely one day. We hope for the best. Thank you, sir. Anything, sir? Any other questions, sir? Sir.
Duration is also an issue. You be surprised that phenomenon like grief and fatigue, they are for only 1 lakh. Although we are getting life much more than that, that is because the margins they have given in the exam. But otherwise, there are 3 factors which are considered in design. One is pressure, and temperature, and third is the time. Time is only 1 lakh. If you can go back and check the time. The time is only one. For phenomenon like grief and fatigue, only 1 lakh hour is considered. Although the BSL supplies boilers have run for 30 years. But time is not more than 1 lakh. And some of the things we don't describe in our specification. And that is why designers take the liberty to make it as cheap as possible. So see, if you have not written in your specification that whatever be the condition of operation, there should not be any boiler to pay. He will not make. Why he will not make? Because cost will go up. And then he will not get the order.
Thank you.
Sir, my name is Raju and I am from JSW Sambalpur. And it's been only 3 months of joining JSW. And actually, I was previously in LNT Rajpura, the same make boiler which you are talking about.
Yes.
So I have worked in this type of boiler as an operator engineer. So apart from all these things which you have taught, I will share my experience as an operation engineer. In this type of boiler, there is one clear or you can say different thing is that in second pass of the boiler, there is a provision of back pass temper, which actually segregates the by operating the back pass temper, you can manage the flow of flue gas through reheater and superheater. So initially we have also faced a lot of problem like reheater temperature middle excursion and boiler to decay. After a rigorous 2 to 3 months of boiler tuning, like optimization of additional air damper, which you have actually pointed out in your presentation, optimization of additional air damper and backpass damper has substantially reduced the boiler tube leakage and middle temperature excursion. So I would like to add all those things from operation point of view.
Thank you.
This boiler is different from other boiler in a respect that it has 2 firewalls. I have also worked in Tata Power Mundra 800 into 5 megawatt. In that type of boiler, there was only one firewall. So in this type of boiler, which we have told this like boiler, the temperature controllability and uniformity is more. You have more control measures and tools.
Okay, thank you, sir. Actually, this is the Rajpura boiler is the first phase boiler actually. So definitely there is a chances of improvement. That okay, sir. Thank you. Thank you, sir. Okay, sir. I think. Thank you, sir. Thank you for giving me opportunity, sir. Thank you.
Thank you very much for your colorful presentation, sir. In fact, it was in detail. Due to time limitation, we could not able to listen to that every information what you contained in this PPT. It was touching about the stress corrosion and creep failure and various damage failure for BTL and the challenges faced by dissimilar welding as well as the solutions how to overcome these problems faced in dissimilar welding. And you have also shared these wonderful case studies of boiler tube leakages. Thank you very much, sir. Now the session is
closed for lunch, and again we will be assembled back by 2:30. Is it okay? Now it is
Recording stopped.
1:45. Is it okay? Can we assemble back by 2:30? Yes, the online participants also can get disconnected. Again, you can assemble by 2:30. Thank you very much.
हाँ, लंच की सबकी व्यवस्था जिप्ट हॉस्टल में की हुई है। हम सब लोग साथ में ही जिप्ट हॉस्टल जाएंगे, वहां से लंच करके ही वापस आएंगे। इट्स ओके? क्योंकि इसके बाद के काफी प्रेजेंटेशन बहुत अच्छे प्रेजेंटेशन है, और प्रेजेंटर से मेरी रिक्वेस्ट है कि उनके जो प्रेजेंटेशन है वो हमारे जो IT क्यूबिकल है वहां जमा कर देंगे। दे में शेयर विथ मेल आल्सो। थैंक यू वेरी मच।
Recording in progress.
The speakers to present that presentation. Please, sir.
So, good afternoon, all. So, as mentioned, that my presentation will be on the corrosion of boiler tubes and strategies of prevention. So, before we start the presentation, I would like to just give the brief introduction about the collaboration between IIT Bhilai and JIPT JPL. So, I mean, we met Mr. Ramdas Katre, and after our meetings, we had a couple of visits. I mean, he kindly visited our institutes, IIT Bhilai, and then discussed about the collaboration with IIT Bhilai, and our team also visited, and then Katreji kindly hosted us last year. And then later on, Director JIPT and Katreji visited IIT Bhilai again 1 month back. I mean, we had further collaboration, and perhaps, I mean, in the month of November, we are going to have one conference on green hydrogen energy, okay, in either Raipur or Bhilai. So we hope this collaboration will foster further. So as part of that, I mean, we thought of talking about this prevention strategies of this boiler tubes, okay, and where IIT Bhilai can collaborate. I mean, through R&D, they will try to give some solution so that these problems can be attempted and resolved. So as far as our presentation is concerned, we will jointly give the presentation. And before I hand over the presentation to my colleague, Dr. Purnendu Das, I would just take 5 minutes to quickly talk about various corrosion processes that are typically encountered. Okay, and then he will talk about the specific corrosion taking place for these boiler tubes and their implications, outcomes, the problems, detrimental aspects, and then the prevention strategy. So okay. So very simply said, that corrosion is a deterioration of metal resulting from the chemical attack by its environment. And if you see the boiler tubes getting corroded is basically because of the environment, high temperature, and then pressure, then various other chemical environment, so that leads to the corrosion of boiler tubes. And then rate of corrosion depends upon the temperature and concentration of reactants and products. And metals have free electrons that set up the electrochemical cells within their structure. And metals have a tendency to go back to a low energy state by corroding. And that's how the corrosion starts and propagates. So apart from galvanic corrosion, which is well known, I mean, let us talk about the grain boundaries and grain boundary corrosion, okay, and formation by formation of electrochemical cells. So these grain boundaries are more anodic in nature, and therefore hence gets corroded by the electrochemical attack. So, I mean, you know, from the fundamentals of corrosion, I mean, this is primarily by the anodic dissolution. Okay, the metal gets corroded, through anodic dissolution in presence of the electrolysis that takes place under the suitable environment. That means when there is a electrolytes, then there is a cell formation, electrode, cathode and anode, then this corrosion takes place. So, but then, there are different types, and in the micro level, when we see the corrosion taking place, and then they nucleate and then further propagate. Okay, it starts with the grain boundaries. Okay, and then grain boundaries are at the higher energy, and then impurities within the material, they actually migrate to the grain boundaries. As shown in this. And this microstructure, they're showing the grain boundaries. And then this solute segregation actually might cause the grain boundaries to become more cathodic. And that's how this, it leads to the formation of the conducive environment for corrosion that can take place. So this is the schematic representation how these grain boundaries become the anode, and then corrosion starts and then propagates further. Okay. If you see the, when we talk about the grain boundaries, there are multiple grain boundaries formed by the different phases. Okay, that's what we talk about, this multi-phase electrochemical cells formation. And that, but then the mechanism remains same. In multiple alloys, one per phase is more anodic and than the other, and the corrosion rates are higher in the multi-phase alloys. For example, in pearlite gray cast iron, and these graphite flakes, okay, is the cathodic, then the surrounding pearlite matrix, okay, and then the anodic pearlite phase corrodes. And then in steel, in martensitic condition, after quenching from austenitic condition, has the better corrosion resistance. And therefore, we talk about this austenitic stainless steel getting being more corrosion resistant. Impurities in metals actually leads to the precipitation of the intermetallic phases and hence forms the anodic and cathodic regions, again leading to the corrosion. There is again pitting corrosion. Is also one of the important aspect of corrosion which takes place during the boiler tubes, in the boiler tubes. So basically, the localized corrosive attacks that produces holes or pits in a metal, and that results in sudden unexpected failure as pits go undetected, covered by the corrosion. So this is very harmful. It's like cancerous cells. So this pitting corrosion. When we never know, we cannot detect when it develops, okay, and when it further grows, propagates into the macro, having the macro features, then only we are able to we are aware this, yes, this corrosion has taken place. We try to prevent it, but then enough damage has been done. It has penetrated deep inside. Okay, so so this is the pictorial representation of how, of course, the amplified view of this pitting corrosion. And this pitting actually requires an initiation period, what I was talking about, and then grows in direction of the gravity, and then pits initiate at the structure and the composite heterogeneities. Then this growth of pit actually involves this is the schematic representation, how this electrochemical cell formation takes place during the pitting corrosion, and then how it grows, involving dissolution of the metals in pits, maintaining the high acidity at the bottom, and then anodic reaction at the bottom, and then cathodic reaction at the metal surface. Okay, therefore we get the impression that the surface is protected. However, it is not, because a micropits has already been formed microscopically, which is not possible to observe or detect under our bare eyes, and then it has started, corrosion has started. Okay. So and then similar is the crevice corrosion. Okay, then here also it is highly localized form of corrosion, again detrimental. So in crevices and then under the shielded surface, okay, with where stagnant solutions can exist. This occurs under the valve, gaskets, rivets, and bolts in alloy systems in steels, titanium, and copper alloys. And this is how this anodic reaction taking place. This metal, being dissolved into metal plus and electrons, and then in the cathode we have the hydroxyl ion formation from the reaction from the oxygen and the water. As this solution is stagnant, this oxygen is used and not replaced, and these chloride ions migrate to the crevice to balance the positive charge and form metal hydroxide and free acid that causes the corrosion. Okay, so this is about this crevice corrosion, and as you said, the electrochemical reaction, how it takes place. Formation of the hydroxyl ion, then hydrogen ions, and these are all detrimental for the corrosion taking place. Then we have this intergranular corrosion. Again, localized corrosion. Okay, why we are emphasizing showing these? Because these are not macro level. Okay, these if you see the material, okay, microscopically, and then after some chemical treatment, controlled environment, then only this type of corrosions get detected and then revealed. Okay, so again, localized corrosion at the adjacent to the highly reactive grain boundaries, resulting in the disintegration. Okay, so as I was telling, it is part kind of the grain boundary corrosion that I had showed earlier. When the stainless steels are heated to or cooled through this sensitizing temperature range 500 to 800, chromium carbide precipitate along the grain boundaries. Okay, and this is the chromium carbide formation, if you see. And when exposed to corrosive environment, this region next to the grain boundaries become anodic anode and the cathode. And when this anode cathode formation takes place, again electrolysis, again corrosion that takes place. So this is the intergranular corrosion. Then stress corrosion cracking, of course, has been discussed in great detail by my previous speaker from L&T, so I'm not going to detail. Okay, so and then erosion corrosion also has been talked about by him. Okay, this is also very detrimental form of corrosion. We have to first of all understand what is the condition leading to this erosion that takes place. Okay, and corrosion, erosion corrosion taking place. And then followed by the cavitation damage. So acceleration in rate of corrosion due to the relative motion between the corrosive fluid and the surface. And then pits and grooves values appear on the surface in the direction of the flow. And the corrosion is due to the abrasive action and the removal of the protective film, which forms over the metallic surface. And then cavitation damage is caused by the collapse of air bubbles or vapor-filled cavities in a liquid near the metal surface. And then rapidly collapsing air bubbles produce very high pressure and damage the surface. So this is how the erosion takes place. But then this erosion, how this erosion is leading to this corrosive environment. Okay, and then finally the corrosion taking place because of the high velocity flow of the fluid. So then we have this fretting corrosion and selective leaching. So this fretting corrosion occurs at interface between the materials under the load subjected to the vibration and slip. So in the previous slide, we talked about this, basically the erosion, that means the velocity of fluid taking place over the metallic surface leading to the condition of the corrosion. In the next, if you see, it is under the action of the mechanical load, vibration, slip, and that is actually causing the basically the fretting corrosion. Metal fragments getting oxidized and acts as the abrasives between the surfaces. And this selective removal of one material of alloy by the corrosion is called the selective leaching. So example, actually zincification, selective removal of zinc from copper and brasses, and then weakens the alloy. Single metal might not have the same strength as the alloy. Okay. So these are some of the, basic form of corrosion, okay, that you might be already aware of. However, I thought of before going to the, actual corrosion that takes place and how it looks like when boiler tubes are investigated by the R&D team. So we thought of just giving you the brief introduction. Now I hand over my presentation to my colleague, Dr. Purnendu Das. He will take you through the, different types of, actual condition of the corrosion that takes place for the boiler tubes. Some of the things you might have seen already. Mr. Ali from L&T has already shown you those, how, for example, this root cause analysis, etc., through this photographic microscopic investigation, etc. And then we will move further with how IIT Bhilai can pitch in and collaborate to resolve these problems with some systematic approach. Okay, so now Dr. Das.
Thank you, Dr. Gangopadhyay, for giving a nice know-how, the basic know-how for diving into the part of the corrosion. So before going into the corrosion, I would like to reflect on one of the questions raised during the introduction session. Sir has actually asked one question that why this corrosion or why the boiler tube failure is such a big issue, and the designer doesn't they know that what are the loads there. So the issue, I was trying to reflect on that, and what came into my mind is that whatever given pressure is there in a boiler tube, if we have a thickness of 1.5, 2 mm, 3 mm of thickness, that thickness is good enough to hold a huge amount of pressure. But when corrosion starts, the mechanism, as Dr. Shoma was pointing out, mechanisms like crevice corrosion, stress corrosion, cracking, or pitting and all of them don't actually attack the tube from the length perspective. They directly go for the thickness And even a small indentation in the thickness actually creates a high stress concentration in the thickness direction. And now if we talk about the structural stress, the hoop stress that is acting along the wall, that because of this high stress concentration, the hoop stress in that
হ্যাঁ বলুন হ্যালো বাস চলে যাচ্ছে স্যার বলুন মেশিনটা পেয়ে যাবেন তো আজকে মেশিনটা আপনার চলে এসছে বিল হয়ে গেছে ডেলিভারিটা আমার লাগছে আজকে হবার ছিল আমি এখানে চলে এসেছি বাঁকুড়া হ্যাঁ। আমি স্যার নাম্বার আর আপনার প্রবলেম হবে না আজ আমি আপনাকে জাস্ট কল ব্যাক করছি कौन से बोर्ड में करोगे হ্যাঁ করছি না আমি করছি স্যার ফিল্ম মেকার है বেরিয়ে করছি है तो फिल्म मेकर में करो ना नॉर्मल चार्जिंग में डाल दी क्या लगा दी हाँ बैटरी लगा बेटर है कहाँ है इसका नहीं था इस साइड पूरा उधर सेंटर में वहां से एयर इंडिया आता की वहां से नहीं ले जाओ उधर बिल तो प्रो बाकी बस ये मोबाइल एक जगह सेट कर लो एक जगह बैटरी सेट कर अच्छा এই মোবাইলটা রক্ষিবেন মানে ভিডিওটা নেই কি নেই নেবো যেটা কম এমবি আসতো না তোমার মোবাইল বনে গেছে ভিডিও বহুত যাত্রা লেগে সরকার কেন ভিডিও
so So one by one, these failures can happen. First, this creep can be seen, and then probably even if the temperature goes even higher, then this kind of a failure happens. Apart from that, tube failure from dissimilar welds, which is in different tube joints. So that is also option. That is also an site for failure. Deaerators get oxidized, and corrosion starts from there. Apart from this, feed water heater and economizers are also subjected to heat. One interesting observations I found is that the difference between these two things. In one case, the failure was catastrophic, and this is kind of elongated. In another case, even though the separation is there, the spreading is not very fast. So it was identified 2 different type of failure is still possible. In one case, you have slow rise of heat. So this is more because of the thermal damage. And the first one, this image, is more because of the stress. The pressure was on the higher side. So you have the combination of pressure and temperature to make your tube fail. So if the pressure is the more contributing factor, then it is estimated that your failure will be more catastrophic. So I guess a big part of this has already been covered by Dr. Gangopadhyay when he was introducing corrosion. Nevertheless, so I'll just read it out. It says that the most common causes of corrosion are dissolved gases, which is oxygen and carbon dioxide, under deposit attack, low pH, attack of areas weakened by mechanical stress, leading to stress and fatigue cracking, continuous exposure to thermal and thermomechanical stress. So if we look into different locations, there are possibilities of internal pitting at the weld zones, possibility of internal graphitization under the in the insides of the tubes, which is underscale pitting. There is possibility of thermal fatigue cracking. So there is continuous weakening of this cross section. There can be local ash erosion, blisters and pinhole leaks, fish mouth failure caused by hydrogen damage. So once again, hydrogen damage, if you see, there are crack formation within the microstructure. And because of the hydrogen diffusing through these cracks, so the bridging of the cracks is also not possible. So leading to weakening and further catastrophic failure of the sample. Another thing, so erosion, corrosion damage in the inner wall of the tubes. Another interesting thing to note here is that both are the same material tubes. The internal flow has damaged the material, right? But it shows that here the damage is only at a particular cross section, whereas if I see in this bend tube into the bend, the erosion effect is much higher. The horseshoe, so this kind of removal of material is termed as horseshoe removal of materials. So that effect is much higher when the flow is basically encountering a bend, right? So actually what happening is that the streamline nature of the flow is getting disturbed. The flow has to now take a turn. So there's additional force being acted at the corners. Associated with this, there is the erosion, there is the absorbed gases, they are also coming out, and because of which this kind of failure is there. So this is a basic understanding of how the corrosion starts. Chlorine, there is some amount of chlorine absorbed in the fluid. So that chlorine, so what it first does is it reacts with the iron to make it a FeCl2 ferrous chloride salt. Now this ferrous chloride salt very quickly reacts with the absorbed oxygen or any oxygen present in the system, and because of that it forms a iron oxide and chlorine. So now this chlorine, interestingly, is not being released into the flow anymore. The chlorine is now, it is released from the reaction zone, but it is released towards the inside of the material, right? Instead of, so let us say this is our line, this is the gas deposit has happened over here. So any material, so the material is basically below this line, and above is the flow is happening. So the rejection of chlorine happens to an underneath layer, because of which the next layer of iron gets oxidized and the reaction propagates continuously to the subsurface layers. So this actually identifies the presence of chlorine in the liquid that we are using in the boiler tubes. So that can be extremely dangerous. So now, so we as IIT Vilai, so we were trying to reflect that what all actions we can take on this. So how we can look at the problem and what kind of solution we can come out. So the first thing is that we can look into the corrosion determination of the corrosion mechanisms, right? So most of the strategies that we were discussing or that we look for is in situ strategies, right? So but here we are talking about ex situ strategies. These strategies may not be applicable on an ongoing plant or a runtime in the runtime, but if we have sample failure samples or couple of failure event happening before us, we can collect samples, we can look into that and then pinpoint what are the issues happening, right? So kind of root of the root cause, if we can find out, and then we can address that. So what we are doing is analysis of the corroded section of the boiler tubes. So once we start analyzing, we can have microstructural investigation. Apart from that, we can have optical and electron microscopies, surface profilometry, ACM, XRD, and Raman spectroscopy. So all of these leading to identification or pinpointing exactly what was the mechanism for failure. So if whether this was because of presence of chlorine or presence of the formation of the surface layer was there, and then the surface layer has ruptured, or there was a stress corrosion cracking, there was a pitting. So exactly which phenomena has taken place, that can be identified from this mechanism, from this study. Followed by so once we can find out which mechanism was there, that will also allow us to associate that knowledge with which is the probable location for such kind of failures. Let's say I'm saying that it's a erosion corrosion damage. So as we were seeing that, we know that this kind of damage is more probable in a bend of a pipe, right? So once we understand the mechanism very well and we can find out, then we can know that, so we will have a basic idea that if the location of a failure is on a particular section of the pipe, we understand that this is more prone to have the failure type A or B or C, right? So we have a list of probable failures now. And apart from that, we can also have a fluid flow simulation for identification of source of turbulence within the high temperature flows. So I'll just show you, So I'll show you this fluid flow simulation, which shows the variation of the fluid flowing across a pipe tube. So the fluid is moving in upward direction in an aggregate scale. However, you can see there is internal whirls and change of directions within the flow. And because the flow velocities are changing in different directions, so the heat distributions, because the whole principle of boiler is basically heat exchange, the idea of heat exchanger, right? So because the flow velocities are changing in different cross sections, the temperatures are also varying, right? So on the same pipe, on one side we are having a much lower temperature, on another side, because of the variations in flow, we have an extreme high temperature, right? So if our simulation can give us these results, then we have two options now. We can either go back to our design and we can say that, okay, this wall thickness we have to increase, or we have to increase the cooling, or we can the flow design, or we can say that the tube shape or the bend placements are such that it is increasing the heat accumulation over here. So we might have to look into that bend placements. So the geometric shape of the tubes can be played with to change this situation and have a more uniform heat distribution across the cross section, right? So these are some of the basic ideas that we can do once we have certain samples from the failed parts. Next is a very typical approach how we can actually analyze the whole situation. So it's more similar. It's more in the same line what I was discussing. So we have the failed tube. We segregate into multiple sections. From each sections, we find out the cross-sectional micrographs and find out that, so at least from here we can see the section 5 and 6 are showing a different kind of a micrograph. So this will tell us that what was the microstructural or compositional defect that this pipe had, for which this failure has taken place. Apart from this, here there is a scale formation on the inner layer. So once we look into it in a magnified scale and try to have a elemental mapping of it, we will understand that what kind of material loss might have taken place, right? So this scale, this is basically the internal surface of the pipe. So we look into it with a higher magnification. We try to see that whether the oxides were forming or some other salts were forming on the inner surface, and when it ruptured, what kind of material has been removed and what is remaining back there. So we can try to see what is the compositional changes happening over here. Next is from the failure. So this is, we can also look into the fractograph from the failure lines of the pipe, right? So the pipe has torn off from a particular line. So if we look into that, we will see certain types of failures, and there are standard failure micrographs or fractographs in testing of materials. So we can compare and understand what kind of loading was there, whether it's a fatigue loading, whether it's a compressive loading or tensile loading, what was the nature of the loading that we can identify from here. Also, along with this, we can also have the elemental estimation. So here we can see the vanadium was high in a particular section of the sample, some particular section that vanadium is not there, and the iron was high. So this will tell us that what exactly was happening with the elemental part. Apart from this, we have XRD, so we can see what are the phases developed. It may happen that your material that you are subjecting to this high temperature for a prolonged duration is going through a phase change. And because of this phase change, there is certain weakening in the material. So that also can be identified from the XRD. So now, based on all of this, so this is basically snippets of a particular publication by Hagigat and Shishvashan in 2019. So this I just took a snapshot of that, which says the damaged section comprises of a large grains with excessive voids and thin tube wall, along with the ductile fracture and obvious variation in the metallographic and mechanical properties of the cracked region. So this is the statement done in the paper. This is kind of the conclusive statement. But as a part of the academics, we don't stop here. We actually take it to a next level, because once these problems are identified, we have potential solutions also at our disposal. So let us see what are the potential solutions given. As a consequence, few practical recommendations are put forward to minimize the rupture on the superheated tube. What are these? Number one, the use of other types of steels with higher alloying elements. So here, at least in this publication, it is not mentioned that which alloying element is necessary, but looking at the situation, it is possible to designate alloying elements which will solve the specific problem that we are facing. Next is improvement of fuel combustion to prevent reductionary ambience around the tubes to completely burn the fuel. So this probably is coming because there is certain amount of graphitization or carbon deposition is being observed. Number three, the use of the mazout fuel with without or less impurities such as sulfur, or replacing the mazout with pure natural gas if possible. So this is once again a specific comment looking at the involvement of sulfur into the picture. And number four is cladding the sensitive and critical regions of the superheated tube, such as welded sections, corners, areas close to the nozzles with plates that are endurable against higher temperature and corrosive environment. So this idea once again is, as I was showing, in the bent section or in some of the sections where turbulent flow is being established and the temperature is rising. So how to handle that? We can have some amount of external cladding on those surfaces to have some thicker material support over there, and then the high temperature resistant material can be deposited to stop the failure from that. So with this, I will now hand over to Dr. Shomo for continuation.
Yeah, thank you, Dr. Purnendu, for your nice root cause analysis of actual boiler tubes as far as the corrosion is there. I mean, he has gone to very depth into the microstructure and various evolution that you have already seen. And now, okay, so I will talk about now the next step, that is the solution. Okay, so I mean, of course, this is the one of the photographs of the boiler tube cross section. Okay, this is the microscopic picture, and this is the scanning electron microscopic picture. I mean, this has been magnified and then shown where the damage has taken place or the penetrated into. Okay, so and if you see, I mean, there's a, increase in chlorine percentage, which is very substantially high, which is one of the major cause of this corrosion. As the mechanism has been explained by Dr. Purnendu very well. So, okay, so what I was talking about, the possible solution route. I mean, what we can do at IIT Bhilai. Okay, so basically we are. Let me tell you. I mean, the lot of research work is going on worldwide. Okay, various countries. In Japan as well. I was talking to Mr. Ali during lunch. Okay. So they, a lot of prominent and eminent research labs across the globe. They are trying to resolve the problem of boiler tube corrosion by various routes. Okay, but however, among these, industries are also doing, as L&T has demonstrated. So among various routes, we have tried to focus on. We'll focus on two aspects, not all, only two aspects, okay, as the probable and innovative ways of doing that. One is the development of suitable corrosion inhibitors, okay. I will talk about it, and then this development of appropriate surface engineering solution, okay. So let us go one by one. So this chemical corrosion protection, that is the development of inhibitors, okay. Various people have tried, for various application, not just for boiler, but in general for corrosion. And so so these actually, I will quickly wind it up. So these oxygen scavengers, then phosphate inhibitors, filming amines, neutralizing amines, silicate inhibitors, molybdenate inhibitors, they are actually, they have the potential, okay, to, arrest the elements which are responsible for promoting the corrosion. Okay, these are all it is not primarily related to the metallurgy or mechanical, rather it is chemistry. However, this can be one of the potential routes, and IIT Bhilai has the expertise of doing research on that. Okay, so this research team has actually done a lot of good work in development of this chemical corrosion protection through this route. Okay, and then another is the surface engineering. Myself and Dr. Purnendu Das are actually actively involved in the surface engineering for various mechanical applications. Okay, for protection of wear, for protection of corrosion, and various other things. So that way, we can propose certain surface engineering solutions. So basically, the thing that I have shown here specifically. Okay, so this is the tube failure in the boiler. Okay, so this Oksa et al. is from one of the research articles from Japan, and they have actually talked about some metallic coatings. Nickel, chromium, aluminum, yttrium based metallic coatings that can actually act as the potential corrosion inhibitors. Okay, and this has been deposited over the tubes, which are low cost, not very, maybe a very expensive, sophisticated one. Even the low carbon steel can be used as the tube, and then over that we can have the deposition of these metallic coatings, nickel, chromium, aluminum, yttrium based coatings, which will form the protective layers, which will be and which will be sacrificial and also useful in protecting the corrosion. And this methodology, this coating technique is primarily the thermal spray coating. Okay, HVOF based coating technologies, for example. So people have tried out and got various, encouraging results. Okay, I mean cost effective also because thermal spray coating is not very expensive technology. So I mean people have tried. So similarly, we can also try for a boiler tube application if it can. And then important thing is material development. Okay, it is just talking about this Ni24 CR. However, I mean a lot of material development has gone into that after that. So we can actually tap those advanced materials, okay, which can be used as the coating over the boiler tubes for corrosion protection at IIT Bhilai. Now, talking about the facilities, we have actually a lot of, that's when actually Mr. Ali showed various, I mean, testing results. I was actually fascinated and discussing with him during the lunch that, I mean, is there a dedicated R&D lab or not in L&T? So we at IIT Bhilai, we have a dedicated R&D center, okay? And we have state-of-the-art facilities, absolutely, I mean, world-class for investigating various, you know, I mean, this metallurgical investigations and related investigations which will be relevant to this project. So we have this high resolution, high magnification field emission type ACM, which can go up to 2 lakhs magnification or more than that. We have the XRD for detection of phases, crystallography, stress analysis, Raman spectroscopy primarily for the oxidation detection, which is, I mean, one of the major part in corrosion detection. And then we have the optical microscopy metallography lab. We have the contact and non-contact type surface profilometer. This is very important because where, I mean, these micro features, micro channels have been developed because of this corrosion can be effectively obtained. Then we have this digital image correlation facility, IR camera, electrochemical workstation for evaluation of corrosion, and then UTM, okay, for evaluation of material properties, strength, etc. And then mass spectrometer and a sputter coating deposition system. We have, as I was telling, that I mean we have expertise okay, available to deal with this problem, because I mean, as Dr. Purnendu has said, I mean it is just not the chemical analysis. I mean there is metallurgy involved, there is a mechanical analysis involved, and then there is a computational fluid dynamics involved, right? So I mean some faculty members, as is mentioned, are expert in the fluid flow analysis, fluid dynamics, computational fluid dynamics, through which we can actually, I mean, simulate the entire thing which is taking place within the boiler tube, and then pinpoint the problem areas which can potentially lead to the corrosion in actual environment. Okay, and then I mean this is the starting point for the people working in the field of coating or metallurgical aspects, etc. So just for information, our director, Professor Rajiv Prakash himself works in the corrosion, and he is basically the expert in corrosion chemistry, the thing that I was showing, the I mean for corrosion inhibitors. He has actually developed a lot of inhibitors for the industry, okay, I mean some 5-6 years back. So and then these are the I mean other faculty members and their expertise. So that's all from our side. Thank you. And if you have any query, please feel free to just let us know. But then again, afterwards also I will be, and we will be happy to interact with you, address your problems. Yes. We have, as you said, that all mechanical characterization and metallurgical characterization, we have all the facilities.
Combustion system.
Combustion system, I'm not very sure. Combustion.
Fuel testing facility we have.
Okay. Yeah, some fuel system characterization testing setups we have. However, detailed combustion, I don't know.
Research going on in alternative fuel development.
Coal combustion. No, I don't think coal combustion setup we do not have. Yeah. I mean, just simulation domain we are working on, not the actual experiment. Yeah. Any other query? Okay. Thank you again for your kind attention.
Thank you, professors, for giving wonderful, elaborate presentation. It was very educative. giving all insights about these corrosion, different types of corrosion and corrosion mechanism which takes place in boiler, as well as giving this research analysis approach to identifying these root cause for the boiler tube leakages. And you have also given opening option for the way to get united or collaborate with IIT and the facilities which is available at IIT. Let us look for mutual collaborations, and it will be going to be a win-win situation for both academic as well as industries. So with this brief note, the next session will be handled by Mr. Abhishek from Adani Power Limited. He is a senior manager working in maintenance department, having experience of around 18 years. So the session will be sharing experience of Adani, experience on boiler tube leakages sharing. So on behalf of you, I invite Mr. Abhishek and his colleague to deliver the presentation. Please, sir.
Thank you, sir. And first of all, I would like to thank you, JPL management and Chaudhary sir, to giving this opportunity, and always Chaudhary sir guide us for all BTF during the BTF. So as our boiler and even here in periphery, all boiler are same like BHL 600 megawatt boiler. So I just want to share my experience, what is the failure we have means occurred in our boiler, and what is the action plans we have taken during these failures. Our back pass bottom ring header. This is the support tubes from economizer coils that's connected to this header. Na? So this is the basically the erosion failure. So what we have done, we have just placed the sealed, and the root cause was we found out during the overhauling and our routine maintenance. During the inspection of the coil by gapping the coil. So after inspection, there is no provision of the locking in the economizer coil to coil. So that's why this not come in the original place. So maybe the gap will increase in that area. So the flow will increase. That's why this failure happened. And this is for erection weld joint failure. We have occurred this failure in the economizer. Even our thread area is the bottom of the economizer. We are facing more failure in this. And this is also the well-known failure in burner area. We have applied the plastic refractory. So one of the bent portion refractory peel off, and due to the secondary air flow, the burner tube, first tube of the burner panel got eroded. Same, this is the eco inlet header connection tube. This is also due to the erosion. It is the second number coil of the right side. Actually, we have what we have done. We have complete the full shielding of 4 coils, both side LTSH and economizer. But the connection joint, it was left for the shielding, so the failure occurred. And this failure in the reheater coil, and the root cause was identified by the Chaudhary sir. Actually, this is for the because of the soot blower. The top of the soot blower in the reheater zone, the slope is not the proper in the soot blower piping. So the condensate, while the soot blowing of this condensate impinge on the tube. So this is the crack occurred in the tube. So for this prevent, we have identified the action plan in this visual inspection, shieldings, And for well joint failure, the proactive RT, we have already taken in the opportunities. Proactive RT we are doing. And for the burn panel, so we are now we are doing the plastic factory. Again, we are going to the plastic factory, but this time we will weld some anchors if possible in that area. These are some action we have taken during the BTL. So these are major activities we have done in COH also. We have included in this presentation. So the major threat area in our boiler is the screen tube area and economizer area and burner panel. And there is no leakage in superheater till now. So we are lucky. Thank you.
So any questions? The session is open for discussion. If you have any questions, you can ask. Okay, thank you very much, sir. Thank you very much for sharing your experience, valuable experiences. Now we'll go for this third session. The third session will be presented by Mr. Manoj sir and Mr. Tapas Mishra from DCPP. I request Mr. Manoj sir to deliver the presentation.
A very good afternoon to all, distinguished dignitaries, respected all the HODs, and all my dear seniors and juniors. First of all, I would like to extend a very warm thanks to JIPT for providing us this opportunity. And to begin with, and like in the morning session, we were discussing about the availability of units. That is the major concern. And we, DCPP, Donga Mahua Captive Power Plant, being the captive unit for JSPL Raigad, the steel production unit, for us, availability is the major concern, because if we are losing, we are unable to produce power, there will be a huge loss to the steel production, which is our major concern, and we cannot afford to do that. So basically, our major concern is availability that is directly proportional to the boiler's availability, and the main reason for boiler loss is BTL. So here we are discussing about BTL, that is, it's not working. Okay, it's okay. It's okay. Before that, I would like to I'd like to make familiar you all about CFBC, that is circulating fluidized bed combustion. This is a specific technology that we use. Our boiler is CFBC, where you can see that pointer. Okay, so our major specification is this. The boiler that is, you can see here, the coal, that is our fuel, is actually fluidizing here. Fluidizing is resting on this bed that we make a bed, and our fuel fluidizes here with the help of air, with the help of flowing air. And we have this cyclone where the ashes, they just return back, and we have a very less loss of our bed. So this is a specific technology that we use, and rest all are similar for all of us. The only extra thing is that this how our statistics has come from since 2011 to till 2023, and some of the development and the strategies that we follow. These are my table of contents. These are the mechanisms that we usually experience: external erosion, corrosion, overheating, welding defect, fatigue. These are all the types. And here is the statistics that says that since financial year 13-14, like you can see in the graph, we were having number of tube leakages, and from there, and after the financial year 15-16, 16-17, we have tried various methods to decrease it, and now we are having per unit on an average of 3 to 4 BTL per year on an average per unit. That we have achieved this milestone. We believe from coming here from 20 to being here at 5 is a milestone for us. And these are all the pictorial views that we have, the real pictorial views of our BTL that we have experienced. This was due to sand erosion. The sand we use as a bed material in our circulating bed, fluidizing bed. This is a picture of attachment failure. And then flue gas erosion, here we had and then air erosion, overheating. And this was the mechanism. Our main problem is flue gas erosion. Here, like you can see, in the previous consecutive financial years, the major fault that occurred in our plant was flue gas erosion. So we have adopted some of the strategies and modifications that we have done in order to reduce that numbers. So here they are. Like in the steam cool wall of economizer and final superheater, there were notch were being formed. And to reduce that, what we did was we removed the fins plate and we applied a refractory lining to that, which ultimately gave us the result. And next was this furnace sidewall erosion, same refractory lining that we applied. Like you can see here, all the affected wall tubes, 1.5 meter in vertical length has been covered with Acomon Plus 80 refractory with 60 mm thickness. And this was eroded tubes, and we replaced it with refractory lining here, as you can see. And this was shield. An innovative idea that we did in our steam cool panel was providing shielding. Yeah, here, like we had there's a gap. I'll show you this in the another PPT. Here, like you can see, the coils where there is an interface of two, either final superheater or steam cool wall. There is an interface where there was a chances of erosion. What we did was we provided a shield. We provided shielding over there to reduce the erosion and the gaps that could make the erosion. So here, shield was there was no gap left between shield and the fins. Here also, fins projections removed. We removed the area. This was the route of the route where erosion was mainly occurring. So we removed it to avoid the notch formation. And here also shielding, we provided yes, steam erosion because of soot blower that we were facing, the steam erosion. Here also in the reheater coil bank, we provided a shield. Here the problem was that due to direct steam in pigment from the soot blower, wall thickness of reheater tube was horizontal plane is getting reduced by 0.25 mm per year. So we did shields. And what we achieved was reduced number of BTL in that particular area. The same that I discussed earlier. And this was sagging near cyclone inlet tube. Okay, sir will explain it better, I think.
So this is the, this one, no?
Ye wali.
This one. So this is the major concern area in CFBC boilers. In cyclone inlet, there are two vertical bull nodes each having 3 tubes. During after installation, we have faced that कि particular area में जो हमारी ट्यूब थी वो हम चेक कर रहे थे कि after certain time due to maybe certain expansion issue and the other, उसमें बो टाइप बन जा रहा था और उसके बीच से पीछे से जब फ्लू गैस इंसर्ट हो रही थी तो वहीं पे हमारे इरोजन आ रहा था और ये पर्टिकुलर हाइट है अप्रोक्स 34 मीटर और इसको अटेंड करने के लिए कम से कम भी 4 डेज हमको वहाँ लगता था क्योंकि CFBC बॉयलर में मेजर कंसर्न है BTL को अटेंड करने के लिए ये जो इसके अंदर मैक्सिमम है रिफैक्ट्री एरिया है और रिफैक्ट्री एरिया जहाँ रिफैक्ट्री टोटल रिफैक्ट्री हीट कंटेंट रखता है वो इतना जल्दी ठंडा होता नहीं। उस कंडीशन में हमने काफ़ी ब्रेनस्टॉर्मिंग किया कि क्या करेंगे, OEM से डिस्कशन किया तो कुछ भी उन्होंने सॉल्यूशन दिया नहीं और ये हमें सभी बॉयलर में रिपीटेटिव नेचर में आ रहा था। तो हमने उसको टोटल यहाँ पे जो रिफैक्ट्री है वो आप एक 220 mm का थिकनेस है वर्टिकल बुल नोच में, उसको हमने ब्रेक किया। उसमें देखा कि इसमें रीजन क्या है, देखा अनइवन एक्सपेंशन था। उसके बाद फिर हम दोबारा से रिफैक्ट्री लगाया लेकिन सेम नेक्स्ट आफ्टर 6 मंथ बाद सेम वहाँ पे लीकेज हुआ और अगेन प्रॉब्लम सोल्व नहीं हुआ। उसके लिए फिर हमने नेक्स्ट एक यूनिट 3 में लास्ट ईयर कि हमने तो कि इसको तो एलिमिनेट करना ही है। उस कंडीशन में हमने सभी 3 ट्यूब को उसमें से रिमूव किया और उसमें फ्लेक्सिबल सपोर्ट हमने दिया कि जो बो टाइप बन जा रहा है उसको हमको रिमूव करना है। अगर वो बो टाइप नहीं होगा रिफैक्टर भी अपने इंटैक्ट रहेगा और फ्लू गैस पीछे से इंसर्ट ना होगे, उसमें इरोजन नहीं होगा। ये मॉडिफिकेशन करने के बाद में लास्ट 3 ईयर से यहाँ पे कोई भी लीकेज नहीं, तो ये सभी बॉयलर में किया है। इसके कारण में हमारी एबिलिटी भी काफ़ी बड़ी है और ये प्रॉब्लम 100% एलिमिनेट हो गया। अभी सेम हम ये अंगुल में भी इसको इम्प्लीमेंट कर रहे हैं। प्लीज सुधा।
And here was another problem that division wall tube जहाँ पे where we were over the problem of overheating we faced, and there we replaced the material. We used a new material that was T22 just to reduce the BTL in that area, maybe because we were thinking that it's because of overheating, that's why. And next was a new thing was economizer bent cassette baffle. We inserted baffle in that economizer area. Maybe Manoj sir will explain it much better.
इसमें भी क्या हो रहा था सर कि जो सेकंड पास में है इको 1 के बॉटम एंड 2 बैंक हमारे इको 1 बॉटम एंड टॉप, वहाँ पे कैसिंग एक्सपेंशन इनप्रॉपर होने के कारण में गैप इनप्रॉपर हो रहा था, वेलोसिटी बढ़ रही थी और बैंड शिल्डिंग लगाने के बाद में भी काफ़ी लीकेजेज आ रहे थे। उस कंडीशन में क्या किया हमने, ये भी लास्ट यूनिट 2 में ये कैसेट वेफल हमने लिया। ये मटेरियल MOC है 304, अभी 1 यूनिट में अप्लाई किया है। आफ्टर 2 ईयर यूनिट 2 में पर्टिकुलर इको 1 में बैंड में नो एनी लीकेजेज है, तो ये भी एक अच्छा मतलब इम्प्रूवमेंट आया है। तो
And because all the strategies, maintenance strategies that we applied here as a result of consecutive last 3 financial year, that we have reduced our number of boiler tube leakages to 0.64. That is a number of tube leakage per 1,000 running hours. Like our unit depends on running hour, how much running hours it has, the unit has. So based on that, we calculate this the station performance, that is 0.64. And the previous one were 0.7 and 0.72. And this is a learning from failure. Like we were analyzing all the what can be done and what have been the issues of that. So based on that, what we are here concluding, we analyzed is that once our unit has run up to the 5,000 running hours, and we take an overall after 8,000. So what we do is after 8,000 running hours, we take a overall. So based on our analysis and all the facts and figures, we analyzed it. And then we came to the conclusion that if we take a short shutdown, after it completes its 5,000 running hours, we'll be able to decrease the number of BTL if we take a long time to do the overall. So this was our analysis, and based on that, we had some figures that it says that once the unit has crossed the 8,000 running hours, so the number of BTL will increase. Like in the same we can see in unit 4 also. Once it crosses 8,000, we get more number of BTLs. And within 5,000, if we make a shutdown within after 5,000, so we'll get like you can see in unit 3, we have tried this strategy. We followed this, and we can see the results in unit 3. And we have tried to do this for all our 4 units, that will take a short shutdown between once it completes its 5,000 hours. So which will in return will give a long life to our boilers.
For 5,000 hours, we are taking only for 10 days shutdown only. For checking the second pass inspections, if any notice is there, then if any shielding removal is there, then we can do this. We can do right now. We have done in unit 3, so only one leakage is there entire 1 year, and unit 4 is 5, unit 1 is 12, something is that. So right now we are planning to take shutdown for after 5,000 for 10 days only.
This was all. And here we conclude, like what I was saying, that for better performance, we must go for one shot after 5,000 running hours, which in turn will improve the boiler life. This is what we want to conclude here. And that's all. Thank you so much for providing us this opportunity. Any queries maybe?
Any questions, please? Any questions? Thank you very much, sir. Thank you, madam, for giving such an wonderful presentation from JSPL. And Mr. Manoj sir is working as a maintenance head, having more than 20 years of experience, and is having his very good team, adopting the various strategies in arresting these boiler tube leakages. And it was giving a different perspective, especially in approach with that boiler tube leakages from CFBC perspective. So congratulations, sir, for your achievement. And now we will break for this tea. And after tea session, we can come back after 20 minutes, 15, 20 minutes, we can come back. Please, you can leave for a tea break. After completion of this tea, you can join for the session.
Recording stopped.
Would you like to tea? Brother, चाय तो पी ले भाई, बड़ी मुश्किल ला रहा है चाय, दूध वाला है भाई, थोड़ा मना किया ना, मना क्या है।
Good evening. So you are hearing about BTL action plan. Now I will try to hear from you. What are your experiences of failure? What you think about failure? So we'll start that way. Next slide. So,
Recording in progress.
Slideshow. What slideshow?
next slide. Okay, sir. BTL में I'm showing the photograph. Tree. Are you seeing this tree? The बगल में लिखा है struggle for survival. The basic idea, what do you make out of it? इसका दिखाने का क्या मकसद है? Basically, as Chaudhary Sahab has told in his presentation, that it is a lot of pain in a tube to take to fail. A lot of pain before failing, a tube takes a lot of pain, then it fails. It is not a easy task to fail. Don't understand that tube failure ho gaya. Before that, a lot of effort from the tube also goes in to not to fail. Then it fails. It overeats, it swells, there is shrinkage mass, or there is erosion. 5 mm tube goes up to 1.6. We have, Chaudhary Sahab and us, we have done an experiment that at what thickness it fails. And the tube fails at a thickness of 1.6 to 1.7 mm. From 5 mm, it fails to, goes to 1.6, then only it fails. So how much effort, how much pain it takes before failure. So that tube also struggles for its survival. Then it fails. So how much, what are the deviations, as Chaudhary Sahab was telling, either operation or chemistry or ash or coal, so much of deviations goes into a tube failure. It is not, tube failure is not going off its own. So the idea of this picture is that. Now, let us start from all of you. What is the most common cause of failure, tube failure? You have to tell. Everybody? Next. What do you think the next major cause of tube failure? Overheating, we can say. Next. Corrosion. Next. Stress. Attachment. then joint failure. So these are some of the commonly cause of failure. Now, why erosion? Why the erosion test? You tell, why? Erosion failure के क्या कारण है? Velocity. Then high ash content. Unequal velocity or high ash content. Particle size. यही है जनरली. तो वेलोसिटी हाई क्यों होता है? कुछ तो डिजाइन होगा. ऑपरेशन डेविएशन. क्या ऑपरेशन डेविएशन होगा? एक्सेस एयर एंड एक्सेस एयर, एक्सेस कोल तो इसमें आ जाएगा. एक्सेस एयर है, मतलब अननेसेसरी एयर अगर हम दे रहे हैं कि कंट्रोल इट, देन द वेलोसिटी विल बी कंट्रोल्ड. यस. तो क्या आप लोगों ने कभी ऑब्जर्व किया है आपका जो इरोजन फेलियर है, इज इट यूनिफॉर्म अक्रॉस द सेक्शन? नहीं. So there is a velocity, and generally where the failure occurs. Generally, what is your observation? Manual or bends, screen tubes, left and right. But ऐसा तो नहीं होता है कि वो total boiler fail इरोज कर रहा है. नहीं होता है. Then comes the high ash content. ये दोनों कहीं interrelated है. हाईएस्ट कंटेंट है, फेलियर हो रहा है, बट वो लेफ्ट राइट में हो रहा है, बीच में नहीं हो रहा. क्यों? तो इज इट ए रीजन, मेन रीजन, और इज इट द रीजन? Combination of both, yes. If the velocity is the ash content is say 5 to 10%, then high velocity will not affect the tube failure. Yes, है ना? But if the high ash is more, then this velocity will affect. Yes. So what to do? Then somebody told particle size. Yes. How to control particle size? Mill fineness. Then you have to maintain your mill fineness to maintain the particle size, which is in your control. Design जो हुआ है वो तो हुआ है ना? So now you have to see the mill fineness also. So what is in your control, which you can do? Velocity and mill fineness, and if possible, ash coal as per design, जो कि possible होता नहीं है, जो मिलता है वो जलाना पड़ता है ना? तो क्या बचा हमारे हाथ में? वेलोसिटी एंड मिल फाइननेस. तो हम क्या किस पे काम करते हैं? बोलो भाई, जेपीएल बोल दो पहले. कर रहे हैं. So I think normally we are not working on it. Measurement itself is wrong. Most of you are doing cyclone measurement, which is wrong. We should do for isokinetic sampling, either ASTM or better है कि ISO में जाए, and we maintain our mill fineness. So this, how much it will help, you know? किस तरह से आप लोग इतना पीछे पीछे क्यों बैठे हो यार? बार बार मुंडी ऊपर नीचे करना पड़ता है. आगे आगे बैठो हैं, सारी सीट खाली पड़ी है आगे. क्यों भाई? मेरे को बार बार ऊपर नीचे देखना पड़ता है. अच्छा, मेरे को तो नहीं दिखता, मैं नहीं देख पाता ना. बताओ कि मैंने क्या पूछ रहा था? मिल फाइननेस के एक तो फाइननेस एक एडवांटेज है, दूसरा एडवांटेज क्या है? हैं? तुम ही बोलता रहेगा यार. बोलो भाई. कंबशन का क्या एडवांटेज होगा? बेटर कंबशन का क्या एडवांटेज होगा? your fly ash quantity may reduce, your bottom ash may increase. अगर higher level में burn होगा तो ash will go over to the second pass. Proper जगह पे burning होगा तो your bottom ash quantity will be more and your fly ash quantity will be less. सही है गलत है? So that is another advantage of combustion of reducing the fly ash quantity. Question कर सकते हो, free हो. You can question. अब आता है velocity. Next करो यार. मैं करूँ. आ गया. और आगे करो. और आगे करो. वही ले जाओ इधर सीधा. बाद में. Next. आगे. Next. और आगे. और आगे. वो था ना तुम्हारा प्रेजेंटेशन. आगे जाओ. हाँ, बस इसके पीछे जाओ. पीछे. अरे आगे थे. Next. Yes. Now we discuss the velocity. इसका next करो. तो side panels में gap सबसे बड़ा erosion का कारण है. Flue gas tend to rush with the where the resistance is minimum. जैसे हमारा इलेक्ट्रिक करंट में क्या होता है, आप एक लेस रेजिस्टेंस का वो लगाओ, एक हाई रेजिस्टेंस का लगाओ, तो किसमें करंट ज्यादा फ्लो करेगा? लो रेजिस्टेंस. तो यहाँ भी वही है कि वो लो रेजिस्टेंस पाथ है, ऑब्स्ट्रक्शन नहीं है, तो फ्लो वेलोसिटी विल बी हायर. फ्लू गैस विल ट्राई टू पास थ्रू दैट पोर्ट. होगा ना? चलो नेक्स्ट दबा दो इसको, प्रेस करो. So this way the velocity will try to be more on the left and right. Next. So what we have done rather, I think we and Chaudhary sir together, we have done first in Badarpur boiler way back in 95-96. That we have put a rolled wire mesh in that area. We have done it. I'm not just saying here, we have done it. And after that, this is not obstructing the flow. This is diffusing the flow. This is otherwise, if you put a screen over there, then it will deflect. Then in that case, instead of 1 and 2, it will start eroding 3rd and 4th. That's why it is a mesh. There will not be any accumulation. It is a diffusing. It is not restricting. So there will not be an ash accumulation. There will not be. It will be a loose. It will not be a tight. So that flow is passing through it. Yes. नहीं होगा. It is not fixed. It is not obstructing the flow. It is just diffusing the flow. I give you an घर का एग्जांपल देता हूँ जो मैंने अभी पिछली क्लास में भी दिया. Have you seen in your house? जब आंधी आती है तो क्या होता है? If a door खुला है तो what happens? क्या होता है? सब कुछ उड़ जाता है घर में, हैं? And you put your जाली का door, then what happens? क्या होता है? हवा भी आती है, उड़ता भी नहीं. Simple. That is what we are doing. वो अभी आप यहाँ पर करेंगे तो आ जाना JPL में. वो बॉटम पे सपोर्ट देना है. You have to make a support at the bottom. So you place it. अभी next. So now the flow will be. So this is, I think, the major major cause of erosion in the second part. And in the screen tube, here again in the screen tube also we have observed only in the left and right. Left and right, 3-4 tubes are getting eroded more rather than in between. In between also where there is an opening for going this way or that way in the reed or coil, there in front of that only the erosion takes place. Secondly, when your ash content, your firing is above the, say, slightly above the burner, secondary firing takes place, then more ash content, more erosion in the screen tube. Thirdly, when you, to avoid that screen tube failure, what we are doing is we are putting the shield. And by putting shields, improper shields, the gap between the shield also led to the localized erosion. For that, I think I suggested to use this socket type of shield so that there is no gap between the two shields. Here, I think somebody was telling that we are going to put a cassette wafer. I think we are going to remove the cassette wafer by putting this. Okay, abhi cassette wafer is giving you a benefit. After 2 to 3 years, it will start giving you trouble. These cassette wafer itself will start giving you trouble. The top will get eroded. Then there will be a slit. Inside the cassette wafer, there will be leakages, failures. Or at the back side of the steam cooled wall, it start hitting. Then there will be failure on those tubes. So it will start giving you trouble. Momentarily for 2 to 3 years, yes, 4 years, it will give results, but it will again start causing failure. And if the stations are using somewhere the imported coal, high sulfur content, then the ash get deposited inside the cassette wafer and will start corroding. So anything you still want to ask about erosion? I think you must have understood well erosion. So anything you still want to clarify about erosion? तो अब ये बहाना कि हाई एस कंटेंट है सर, इस वजह से इरोजन हो रहा है, ये सब नहीं चलेगा. सबसे पहला आंसर यही होता है ना, सब डिजाइन 2500 का है, हम तो 2800 का गोल फायर कर रहे हैं, ये इरोजन हो रहा है. तो वहाँ कुछ ऑब्स्ट्रक्शन होता है, तो बोला ना, जैसे फॉर एग्जांपल पीछे जाना है थोड़ा, बैक साइड और बैक और बैक और जैसे वो एरिया है जो टर्मिनल ट्यूब के नीचे वाला जो पोर्शन है वहां मिलता है, because of the arch from this side and your ash is normally at the bottom, so it hits that portion and there middle also you can get it. So there are certain locations where the erosion takes. This is also a prominent location for you. सभी जगह मिलता है ज्यादा, खासकर टेंजेंशियल फायर बॉलर. अरे मैंने बता तो दिया सोल्यूशन. हाँ, शील्डिंग तो है ही, शील्डिंग भी लगाइए, देयर इज नो हार्म इन पुटिंग द शील्ड, बट प्रॉपर्ली लगाइए, बिकॉज समटाइम्स शील्डिंग आल्सो लेड टू द ट्रबल. राइट हैंड में ज्यादा, राइट हैंड साइड में ही ज्यादा रहता है. दिस इज ए पिकुलर फिनोमेना विद दिस टेंजेंशियल फायर बॉलर डिजाइन है, उसमें नॉर्मली यू विल फाइंड ऑन द राइट हैंड साइड ओनली द मोर ash content and more temperature also. आप लोगों को टेम्परेचर भी ज्यादा मिलता होगा, क्यों होता है वो? राइट हैंड साइड में ही क्यों होता है? फायरवॉल का रोटेशन क्या है? एंटी क्लॉक, एंटी क्लॉक, ऐसा ही है ना? तो दिस इज दी जो राइट हैंड साइड है, जो एंटी क्लॉक वाइज में जब उठेगा, whenever something, it is easy to lift from this side, है ना? जब वो सेकंड पास में जाएगा तो मोस्ट ऑफ द टेंजेंशियल फायर की वजह से दिस साइड इज द इजीएस्ट, so this is all heavier particles will be more on this side because यहाँ से जाके उतना difficult है. This is the reason normally which is why the all front fired boiler में नहीं मिलता है ये front rear fired boiler में you will not find this type of problem whether the left and right is same. आपका जो CFBC बॉयलर में भी ये प्रॉब्लम नहीं. और एनीथिंग एल्स? क्लियर हो गया करोजन? ओह सॉरी, इरोजन. अब नेक्स्ट ओवर हीटिंग. वो तो होगा ना. तो आफ्टर ओवरऑल पूरा पूरा बन रहा है ना. आप देखिए ना, फुल start from the first pass itself, the total path you are getting for the high velocity. Throughout right side. Right side में क्यों ज्यादा है वो मैंने बता दिया. It is on the left side also, but less than right. कुछ और लगाएंगे, लग सकता है, ऐसी बात हमने लगाया भी. अब आप सोचिए क्या करना. I have told the reason. Now solution we have to find out. कि इसको लोगों को अडेप्ट करना भी इतना आसान नहीं है. अब जब तक ये माइंड सेटअप नहीं बनेगा we will not be able to adapt. तब तक आप शील्ड करिए and seeing the life of the erosion you have to go for overall. All those measures needs to be taken unless and until we are able to stop it. Next is overheating. इस एरिया में गर्मी बहुत पड़ता है ना समर्स में. कितना टेम्परेचर जाता है सर? 47, 50, 48 है ना. तो क्या बोला जाता है आप लोगों को? पानी पियो, ज्यादा पानी पियो बोलते हैं ना. क्यों बोलते? आप ओवरहीट ना हो जाओ. सेम वे आवर बॉयलर ट्यूब में अगर हीट ज्यादा है और स्टीम कम है, either you increase the steam flow or you reduce the heat. If you want to say over tube, मैं बोल रहा हूँ. तो ओवरहीटिंग का मेजर कारण क्या है? मेजर कारण है कि जो ट्यूब जिस मटेरियल जिस टेम्परेचर के लिए डिजाइंड है उसमें अगर कहीं ब्लॉकेज है, मान लीजिए स्टीम ब्लॉकेज, कहीं कुछ फॉरेन मटेरियल आ गया, कुछ स्टीम फ्लो कम हो गया, हीट उतना ही है, ट्यूब फेलियर. या हीट ज्यादा हो गया, ऑपरेशन वाले को जल्दीबाजी है, हड़बड़ी में ज्यादा कोयला फायर कर दिया और सेकेंडरी फायर ऊपर ही जाके हो गया. क्यों? ओवरहीटिंग. So this is basically a cooling medium and heating medium. So if it remains balanced, then there will not be any problem. If it remains unbalanced, is a partial blockage or होगा, then it will take some more time. कभी ओवरऑलिंग के बाद फुल ब्लॉकेज हुआ तो इमीडिएटली फट जाए. कोई बात नहीं, थोड़ा बहुत डिफॉर्म होगा. इसका भी मैंने एक एग्जांपल दिया था, है किशोर. आपके घर में वो पीला होता है ना दूध गर्म करने का, पानी गर्म करने का, गोल हो जाता है ना नीचे, फिर भी तो यूज करते रहते हो आप. इसका भी ऐसे ही है. हीटिंग है कहीं कूलिंग है तो थोड़ा बहुत स्ट्रेट नहीं रहेगा, थोड़ा बहुत it is not going to affect the performance. unless and until की कोई लीकेज हुआ और उसमें टेढ़ा बेढ़ा हो गया, वो अलग बात, उसमें वॉपिंग हो गया, वो आपको ठीक करना है। अगर नॉर्मल कोर्स में हो रहा है तो ओवर ईटिंग के सॉरी इरोजन के आपको खुद सबको पता होगा विच आर द लोकेशंस वेयर द इरोजन टेकिंग, आने का कोई जरूरत नहीं। ओवर ईटिंग आगे चलो। ओवर ईटिंग के भी फेलियर्स तो आप सबने देखे होंगे, बट रीजन आई हैव टोल्ड दैट इफ द फ्लो इज स्टॉप टोटली then it will be a short term overeating, immediately it will melt and it will go, and if the flow there is a partial flow, then it will be long term eating. Long term eating you will find some alligator type of lines on the tube, and short term eating it will be a thin lip, and long term it will be a thick liquid. Overeating failure. This is also a long-term eating. You can see a lot of lines and how much pain is it has taken to fail. You can see there is a thickness, there is oxide layer from outside, and कितना परेशानी हुआ होगा इसको fail करने में, नहीं? ये this is your short-term overeating. पीछे पीछे. So while doing, as Radhisha was telling that our more than 50% of failures are maintenance. So you must have seen such type of failures after the overall, immediately after the overall. Either due to immediately doing the fast operation, or some material is left out during the maintenance. Tube replacement. गैस कटिंग तो नहीं करते हैं आप यहाँ ट्यूब रिप्लेसमेंट करते हैं? हाँ? बोल नहीं रहा है, हाँ? भाई गैस कटिंग को अवॉइड करना है. गैस कटिंग इन प्रेशर पार्ट्स लीड टू मेनी टाइप्स ऑफ प्रॉब्लम. You have to stop the gas cutting immediately. Only grinder or saw. It led to anything you want to know about the overeating? पूछ सकते हो. Backbenchers, anything? देखो हमारे साथ चौधरी साहब भी है. He is my boss, and you have a very good opportunity to learn. आप लोग बताइए whatever you want to ask. क्यों चौधरी साहब?
Sir, how to usually this maybe the
Overeating is inside outside measurement. एक tool आता है.
Yeah, this we are checking sir. Isolation also we are checking.
Yes, that is the only way to know the overeating. Visually, yes, you can also see if you are regularly going to the body. Not difficult. Just by the color change also you can know. Where is the overeating or where? यहाँ नहीं बता सकता हूँ, but वो blackish भी नहीं बोलेंगे आप. वो जो whosoever is going regularly observing the tubes, he only can tell where is the overeating or going to be.
The color change will be very long term overeating.
Short term will
Short term overeating will be local.
Yeah.
So inside is getting also lead to long term eating. Inside is getting.
Inside is getting. Multiplying. नहीं, otherwise super heater में overheating अगर नहीं होगा, then there will not be a chance of increase of oxide scale unless and until you are using bad quality of spray water. Chemistry. If your chemistry is not maintained well, then yes, there will be deposit in the super heater.
Sometimes this oxide scale can fool you also.
Yes.
Reason is oxide scale has a tendency to get dislodged. It exfoliates. So sometimes if you measure the oxide scale, if it has exfoliated, then you will not get the substantial oxide scale.
But in that case, you should see the thickness also.
So it will give you a wrong picture. The best thing is that you take the effective thickness of the tube.
Yes.
And effective thickness is total thickness minus the oxide scale.
Yes.
That is the effective thickness.
Yes.
This is number one. Number two is, it is not only the oxide scale that weakens the tube. You also have to see the microstructure. So sometimes there can be degradation in the microstructure itself. That means whatever is the thickness that is remaining also may not have the required strength. It may have sufficient thickness, it may have sufficient remaining thickness, but that remaining thickness may not have the sufficient strength. So for long-term overheating, there are two things which you have to measure. One is oxide scale, from which you'll have to derive the effective thickness. And number two, you have to cut the sample and send it to the lab to study the characteristic of the microstructure in order to see that there is no degradation or no micro crack, no micro creep crack which has got developed. So these are the two things which you have to do.
So wherever you are finding the effective thickness is less, then that sample of that tube should be sent for the microstructure examination also. Then next is the corrosion. Corrosion पे मतलब अच्छे presentation हुए, but कारण क्या है corrosion? अरे आप लोग ऑपरेटर्स हो, आप लोग ऑपरेशन मेंटेनेंस वाले हो, आपके लिए एक ही कारण है कि केमिस्ट्री के पैरामीटर, कोर पैरामीटर, बस हमको उतना रिसर्च का जरूरत नहीं है. Whatever has been given in the manual that these are the parameters, core parameters are to be maintained, then those should be strictly maintained. That's all. There should not be any deviation, no acceptance for the deviation. Somebody may explain you क्या फर्क पड़ता है 8.5 है 8.6 है. No, if it is 9.2, it should be 9. And if you people are sensitive towards those parameters, this failure will not be. Simple. हमको इतना एज एन ऑपरेटर, ऑपरेशन एंड मेंटेनेंस इंजीनियर, हमको इतना रिसर्च का जरूरत नहीं है. ना अब हम कुछ कर सकते हैं उसमें. कैन वी डू समथिंग? नथिंग. वी कैन अंडरस्टैंड द फिनोमेना, बट व्हाट इज टू बी डन? To be done is strictly maintain the chemistry parameter. Namaskar. So the basic idea is to maintain the chemistry parameter, no deviation. Corrosion, this much I want to say.
See, there are 5 parameters which you must monitor if you want your boiler to be healthy. Number 1 is pH. Number 2 is after cation conductivity. Number 3 is dissolved oxygen. Number 3 is sodium. These are the prominent parameters which you must chloride.
Chloride.
So these are the 5 prominent parameters which you must monitor if you want your boiler to be healthy from the chemistry side. And every boiler engineer should closely interact with our chemistry people to monitor these parameters. It should be the interest of boiler engineer to know that boiler water chemistry is okay.
And these should all be online, no offline. This should be monitored in the online system. Offline is again the manual intervention. So it should not be a manual. Nowadays, technology available, then why not online? Online is more accurate. You can use offline just to correct online if sometimes some problem is there in the online system. Otherwise, for monitoring purpose, only online therapy. और कुछ? Any doubt about corrosion? दिखाना next year. These are the, you see, this is the failures in corrosion. These are under deposit corrosion near joints. And we were there in Badarpur, and at a time we have observed 40 leakages at a time. At one time together 40 leakages because of the under deposit corrosion.
Somebody was talking about cyclic hydro. Now, we did cyclic hydro both in Badarpur as well as in Tanda. Because in one go, there used to be failure in 10 to 20 tubes. So here we did cyclic hydro to ensure that all the weak tubes are surfaced out. They open up and they are identified and replaced. So this was the occasion when we did cyclic hydro. Otherwise, we avoid doing cyclic.
Cyclic hydro is नहीं करना ही नहीं है. नहीं. If you are not confident of your boiler and you think there will be multiple leakages, then you can do. Otherwise, नहीं करना. Cyclic hydro is not going to help you. It may deteriorate your boiler also. So cyclic hydro is, as Chaudhary Sahab has told, is for this purpose only. Because already some thickness reduction has taken place in many places. And some are going, say, after 6 months, some may go after 8 months. So we want to take out all those tubes at a time so that we get some margin for planning of the major one. Say, after that, we have gone for the replacement of our rear water wall panel.
Normally it will come, जैसे आपने कुछ पुराना प्लांट टेक ओवर किया, सीमापुरी या कलेक्टेना, जो 10-15 साल से नहीं चल रहा है, 4 साल से नहीं चल रहा है, वहाँ टांडा में यही हुआ था.
सर, टांडा में जो हुआ था ना सर, that was not because of कि वो चल रहा था, their chemistry was horrible. Chemistry, देखिए सर, again this is mainly because अभी सीमापुरी में there is no problem. There is no problem in the water wall tube भेजा गया, it is fantastic. There is no problem.
होगा. Normally ये श्योर होने के लिए, जैसे आज एक प्लांट ऐसा हो जो आपने स्ट्रेस प्लांट खरीदा 2-3 साल से बंद हो, तो वहाँ श्योर होने के लिए आप कर सकते हैं कि किस तरह के फेलर
कर सकते हैं, but sir, actually unless and until there is corrosion or there is chances of failure, because अगर एक बंद भी बॉयलर है ना सर, तो उसमें corrosion as such खड़े बॉयलर में होगा नहीं. Unless and until, जैसे अभी आप कोस्टल प्लांट बता रहा हूँ सीमापुरी, जो कोस्टल प्लांट में गया था, there is no problem in the boiler. They have preserved the boiler, I think, with nitrogen capping. Then next, let us talk about joint failure. Is the next one? This is for the purpose of acid cleaning. If your boiler is getting some deposit may take place in between because of some or the other reason. If we monitor it and we do the chemical cleaning and as soon as this parameter is more than that. This is again a failure, corrosion near the joint. Next. You can see from inside. पीछे जाओ, पीछे 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 यार, हाँ चले जाओ, हाँ ये you can see from inside there is pitting, large pits in the water wall because of the corrosion. Next, ये देखिए, ये देखिए. So then joint failure. This is happening mainly because of poor welding. तो मतलब workmanship है ना, और wrong electrode होता है ना, उसकी वजह से भी फेलियर. अगर प्रॉपर आपने मटेरियल यूज नहीं किया देन अगेन इट में फेल. तो वर्कमैनशिप इज वेरी इंपॉर्टेंट फॉर दी जॉइंट फेलियर. अभी भी जो कई जगह भी जैसे अब एक जॉइंट था यहाँ पर देखा, वो वेल्डिंग इनकम्प्लीट था, ऊपर रन ही नहीं था कंप्लीट. तो whenever we are also doing a weld, then welder, we should see that our welder is good and welding is good by seeing the radiography. तो joint failures का major reason is the workmanship और the जो हमने material use किया, that is wrong. Sometimes mix up है या हमने preheating electrode को preheat नहीं किया, low hydrogen electrode, so that also leads to the problem in the weld joint. So we have to see all those things. और कुछ anything about joint failure if you want to ask? Yes, stress में तो करना ही नहीं चाहिए joint. And अगर रूट्स यूज नहीं हुआ है, सब मोस्ट इंपॉर्टेंट होता है एक पर्टिकुलर जॉइंट के फिटमेंट में रूट चीज. अगर आपका रूट यूज नहीं हुआ तो डेफिनेटली इट विल गो लीड टू फेल. यही रुकता है. सिमिलरली अटैचमेंट वेल्ड फेलियर, जब जिसको हम बोलते हैं, दिस इज बेसिकली अनइक्वल लोडिंग है आपका. आपने कोई फॉर एग्जांपल बर्नर एरिया में आपने कोई ट्यूब रिप्लेस किया, आउटसाइड देयर इज ए प्लेट, देयर इज ए सपोर्टिंग प्लेट, आपने काट दिया, उसको रिस्टोर नहीं किया जल्दी. It is around 20 mm thick plate. So wherever you are working, as I think Chaudhary Sahab has in one presentation has told that whenever we are working, we should restore it to the original. जब भी हम काम कर रहे हैं, जल्दबाजी में कोई काम छोड़ना नहीं है. We should restore it to the original. If we have cut some plate, then it should be welded again properly. All support should be welded. And welding we are doing, we should not leave any welding at the tube. Normally what happens, that become a concentration point. The welding should be left at the what we call pin. Scallop plate का welding जब आप करते हैं, तो it should not end on the tube. It should end, scallop should be such that it should end on the pin. And there should not be any undercut. Welding में कोई undercut नहीं होना चाहिए. Pin welding में we should use less thickness of 2 mm electrode. Sometimes we are using a high thickness electrode जल्दी करने के लिए, and it leads to undercuts and there is failure take place.
See, boiler is designed only for hoop stress.
Yes.
If any stress other than the hoop stress comes,
yes,
then the process of failure will get accelerated. And all boiler supports, first thing, they should not be disturbed. In case we have no choice but to disturb them, then we must ensure that they are restored to their original condition. Now, many times there are some tubes which are under stress. When we cut them, they become free. And when we weld a piece, that particular tube doesn't take the load. So mostly it is in the case of loading tubes. So all loading tubes, we must cut after properly holding them, locking them, so that after replacing the damaged portion of the tube, it continues to take the load which it is meant to take. So you have to be very careful regarding the supports which are there in the boiler, the tubes which are taking the load of other tubes, and we must be very careful while replacing those tubes.
Then I think somebody was talking about stuff failure also. Here I would like to add is, as Pradesh was telling, in penthouse also sometimes we are facing that stuff failures. So as he was saying that our attachment weld, for example, the panels are supported separately in VHL boiler. I think in Chinese boiler there is no support given for the coil separately. It is hanging from the header only. But there sometimes because of overheating or because of failure or because of secondary firing, those supports goes and the load comes on the stuffs. Then the stuff will take.
Crown plates are cut.
back करना back again back पीछे पीछे और पीछे चलो देखते हैं एक्चुअली यही होना चाहिए लैपटॉप then it is easy find out. तो वो जो क्राउन प्लेट और जो end plates and crown plate hai, those should be expected and those should be restored. And the loading should be on those end plates, not on the header. Similarly, in the second pass, also the stuff failures in the steam cool wall bottom header is taking place in many plants. So I have told that here also that we should see the proper draining of the second pass whenever we are doing a hydro, or otherwise also that water is getting drained from all sides, all the water wall panels, steam cool panels, especially after the hydro. And if we are doing a hydro after every overall, then there is always a chance of that water remains in the steam cool wall if we are not doing the venting, draining properly. Venting and draining is very, very important for the stuff failures as well as for the joint failure. एक इसमें केस स्टडी है एक डिसिमिलर जॉइंट फेलियर जब हम बात करते हैं समटाइम्स वी थॉट कि डिसिमिलर जॉइंट फेलियर इज बिकॉज ऑफ द metallurgy difference, but this is a unique case study where the failure is due to manufacturing defect. Next, ये एक failure है. This type of failure takes place. This is a DMW joint. This is a T20 material. This is the SS material. So next. So from inside you can see the crack. है ना? So इसमें क्या है? The tempering is been done in the T22 side. When they made the material, they have done the reduction in the T22 side material. तो already जो design thickness से कम thickness कर दिया to maintain it, to do the welding with the SS. तो उसमें क्या है? उस particular portion में where the thickness has been reduced, there was a thick scale from inside because thickness has been reduced. So overheating was taking place in that particular portion. Next slide. So you can see this is the only area where you have reduced the thickness. The inside scale has eaten the material. Hinting at the failure. So this is the micro जो हमने study करवाया. Next करो. Micro feature of the detailed DMW joint. Thick edge structure with signs of low ductility. Circumferential cracking in the ferrite material, मतलब T22 side. Located near a dissimilar weld, formation of upside notch on the outer surface of the tube in the फेराइट मटेरियल मतलब आउटर सरफेस पे भी एक नॉच था उस पर्टिकुलर ऑक्साइड स्केल था ऑन दैट पर्टिकुलर। नेक्स्ट, तो ये जो चैम्फरिंग किया गया है T22 साइड में किया गया, यू कैन सी दैट दिस मटेरियल हैज बीन रिड्यूस्ड फ्रॉम 4.5 to 3.6 to match the SS material, जबकि होना उल्टा चाहिए था। चैम्फरिंग शुड हैव बीन डन इन दी हायर थिकनेस का ट्यूब लेकर के उसमें SS में करना चाहिए था, ना कि T22 में लोड। तो दिस इज ए लाइव एग्जांपल ऑफ सिंगरौली स्टेज 1। एंड फेलियर होने के बाद देन एवरीबॉडी स्टार्ट सेइंग कि इसका लाइफ ओवर हो गया। इट वाज नॉट लाइफ, इट वाज अ डिफेक्ट। You can see the thick tail inside in that particular portion. Next. तो T22 portion में overheating का उस that particular portion में there was an overheating. 1 mm thickness तक का ऑक्साइड लेयर था। ये सेम डिसिमिलर जॉइंट है, सेम डिजाइन ऑफ बॉयलर है। बदरपुर में ये T22 है, ये 304H है। वहां पर उसने रिवर्स किया है, ये जनरल चैम्फरिंग इन दी SS ट्यूब, वहां पर देयर वाज नो फ्लो। नेक्स्ट, ठीक ना, चैम्फरिंग इज इन द 304 ट्यूब, क्योंकि हायर ग्रेड मटेरियल है, तो देयर वाज नो फेलियर। सिमिलर बॉयलर है, सिमिलर डिजाइन है, देयर इज नो फेलियर इन दैट। तो this is a manufacturing defect. Next. This is a chamfering in the T22 side. This is the comparison जो मैंने बताया, the same is the comparison. बदरपुर में अभी 28 इयर्स के बाद भी फेलियर नहीं हुआ और वहां पर 22 इयर्स के बाद में फेलियर होना शुरू हुआ। ये काफी पुराना प्रेजेंटेशन है, बदरपुर तो बंद हो गया, कंपैरिजन तो बहुत पुराना है, बट तो अटैचमेंट फेलियर में भी एक you should not go for a blind replacement of dissimilar metal joints. We should observe them. We should take the radiograph, and based on that, if there is no failure, because again, if we do more work, then there are chances of more failure. As told by Chaudhary Sahab, we should moderate, we should reduce our work, unnecessary work हमको नहीं करना। So blindly, we should not go for the replacement of any area or tube. We should first analyze it, what is required, what is not required. इसमें हुआ क्या था कि based on this failure, what BHEL को अपना गलती समझ में आ गई। Then being an OEM, उसने एक गाइडलाइन निकाल दिया कि replace all the additional joint after 1 year to hide his mistake. And he improved, he changed the design, and he issued this guideline. Change design में failure वैसे नहीं होगा। 1 लाख वाल के बाद आप बदल देंगे तो failure पकड़ में नहीं आएगा किसी को कि दरवाजा मैन्युफैक्चरिंग डिफेक्ट।
See, all welding work in the boiler is very important. Whether we weld the tube, or we weld the support, or we weld the attachment, welding of every component of the boiler is equally important. Therefore, utmost care should be taken while welding the support, while welding the attachment. If we think that attachment welding is a structure welding, support welding is a structure welding, I think we are wrong. Why we are saying like this? Because those supports are taking the load. They are not taking load due to hoop stress, but they are taking load due to dead weight of the boiler component. So they are quite important part of the boiler. Therefore, welding of such supports and attachments should also be done with the same amount of care and with the same amount of quality.
ठीक है. Thank you.
Now the session is open for discussion. If you have any questions, please ask. Any questions? It was already an interactive session. So I think there is no further questions. Thank you very much, sir. Thank you very much for giving an excellent presentation. It was entertaining and it was interactive session. With your deep knowledge and your sense of humor, you have made these presentations very interactive. And it was an investigation, analysis, and a solution-based boiler tube leakage program, where you have analyzed what are the various causes for the failures and what could be the remedial measures to arrest this boiler tube leakage. It was a very investigative analysis. Thank you very much, sir, for giving such new insights. And definitely it will be a takeaway for all the participants and they will try to implement wherever they go. With these few words, we have come to this concluding part of this session. Right. Now, with your permission, may I request our Executive Director, JPL and Head of the Plant and the distinguished delegates to occupy the dais for the concluding session. The most respected Executive Director and Head of Plant, JPL, and distinguished delegates on the dais and of the dais, my dear colleagues and participants from various organizations and dear students, very good evening to all of you. Now we have come to this concluding part of this program, that is valedictory function of this one-day workshop on boiler tube leakage, boiler tube failure mechanism and preventive measures. It was very enriching sessions right from the morning, and there were total 7 presentations from the morning. Morning we had 3 presentations. The first presentation was from JPL, and it was started with a detailed analysis of the tube failures of various units. And it was a very thorough analysis. What is the reason behind these tube leakages and what is the corrective action taken? And the way forward and strategies adopted is excellent. And followed by that session, it was delivered by Mr. Vinod Chaudhary, the former Executive Director, NTPC, giving an insight about the root cause analysis and laying the strategy and setting benchmark for zero outage, forced outages between overhauling to overhauling. Sir, your wisdom and sharing of knowledge gave us a lot of confidence that we can run the plant with zero outages, without any outages between overhauling to overhauling. And followed by, there was the third session presentation from L&T, from Mr. Umar Ali, from manufacturer side, who discussed on the critical materials used in boiler and the challenges associated with the dissimilar welding and the solutions to perform this welding and what are the various tube failure mechanisms, and the case studies have been shared. It was also an excellent presentation. Then after post-lunch, we had 4 sessions, started with a presentation from professors of IIT,
discussing about the corrosion mechanism of boiler tubes and strategies for boiler prevention, and followed by the case studies, various case studies from Adani Power, and the third session from JSPL, which helps to understand the boiler tube leakages, the problems and the solutions from the CABC perspective. It was also an excellent presentation with innovative solutions to arrest this boiler tube leakage. And finally, we had the expert presentation from Dilip Singhania sir, where he has given this insight about the various techniques with proof how these boiler tube leakages can be arrested, and ultimately it can be brought down to zero, as our Chaudhary sir has pointed out. So I hope that this workshop has served an excellent platform to exchange of knowledge and information among the different domains of the people, right from the manufacturer, and that participation from the various power plant having different types of boilers, and the academicians. So it helps to share their perspective of knowledge of related with that problems as well as solutions. So by the way, I feel that this workshop has served a great purpose and left with a great learning and takeaway for the participants to implement in their work spot. So with these few words, I would like to invite our chief guest to address the gathering, to share their valuable experiences about this program. With this, I request our Executive Director and Head of Institute, Mr. Jowhary Saf, to address the gathering. I request our Executive Director and Head of the Plant, Mr. C.N. Singh sir, to give the valedictory address.
First, I really missed the morning session because we have a top management review every Monday by Mr. Gilani, and we prepare for that. So it's a weekly review or very short review. So I could not come. We have one of the most known and best experts in the power sector and boiler field, Dilip, and of course Chaudhary ji, ex-NTPC, I need not give any introduction. So I'll request all of us to find and gain diagnostic approach from what has happened today. As Dilip was telling, going on replacing will not help. So from understanding the mechanism of failure, type of environment you are operating, from water chemistry to coal to operating practice to cyclic operations, we have to come out with the remedial methods and preventive methods, where these tips and the knowledge given by these experts will be the great help. And teams, with request to JPL team and others also, will be always seeking their association on the case-to-case basis. At least our plant, this is one of the most biggest pain point. We lost around 4% availability last year, and this year is 5%. But as I expect, with their knowledge, today's workshop, domain support, and engagement, today review, I have promised on behalf of you that post overall, the boiler tube failure has to be near zero. But it's more said than done. So, but with this workshop, Dilip will be available. We're requesting Chaudhary ji also to associate in the overalls, so that we really reduce our business loss. All theories and thesis has to converge to the business benefit. And we see how we stop the leakages. And for that, for the long-term approach of diagnostic and analytics are required. So kindly, with this now today's knowledge, I'll request work out case-to-case solutions, long-term plans, And I'll request Munish also to keep on organizing such subject-specific workshops here to enrich and enlighten our team, where a lot of still we are on the learning curve, because plant actually started running at full load, particularly stage 2, since December 22. Prior to that, it was 30%, 40%, 50%. So December onwards, we started running more than 85 to 90%. So 5% went because of the tube leakages and 5% because of the schedule. So now real problems will come out. And with the knowledge available, the wise person is person who learns from the mistake of others. So work out a comprehensive program to come out of, if I take total outage of 5%, I think 4.5% in every year is because of tube leakage. There is no other outage. So that is our trouble point. And this workshop should help us to come out of it. This month, 5 tube leakage, 4. Last month, 3. Last year, 27. I was seeing the Angul data, 100. CFBC, उनका startup CFBC है. So number of failures 100. So see the mind-boggling figures. NTPC has matured the processes. Here from last person in the queue who's putting the grinder on making the edge to welding torch to current to electrode to the supervision, a process maturity has to come. Knowledge has to go to the level of the person who's really working in the supervision and passing on there from fit up till completion of the weld, and then loading up the tubes, attachments, supports everywhere. The biggest plight is we know all, but the technician who was working, a fitter who was working, hardly knowledge was there. And without him, you cannot complete. Same way the next line engineer. Because I may be having 40 experience, but if the experience doesn't flow the person who's working, it's useless. It's something like a book lying in the library and nobody's reading. So let us keep on revisiting, revising, and organize one more workshop post Unit 2 overhauling, finding the Unit 2 problems, and based on that, prescription for other 600 megawatt units. Because here 600 megawatt units, they were done in hurry, and they were not run at that load. So we are very relaxed. But aaram se chalta hai. But now load has come. Because we are losing around, if you say the business, around 30 to 5 into 4, 20 to 25 crores every month because of tube leakage. So if you convert these losses in the price numbers, that's what I learned in the private sector. Then you will see how to really focus and spend and come out of that. And as Dilip rightly told, it is not the structure building. Attachment building is not a structure building, or it's not a simple building. So from each step, then operation practices, operation is a key role. Light up में आधा घंटा लेट हुआ तो इतना फास्ट चलो कि सिंक्रोनाइजिंग तो कर दो, शेड्यूल रिवाइज ना कर पाने किसी को पता नहीं चले. सच्चाई तो यही है भैया. हमने 4 घंटे के लिए शेड्यूल दे दिया, 4 घंटे बाद शेड्यूल दिया है और लाइट में थोड़ा लेट हो गया. लेकिन आजकल सब कुछ दिखता है डीसीएस में, एवरीथिंग इज अवेलेबल. क्या में एवरी पैरामीटर इज अवेलेबल है. वो जमाने चले गए कि एमटीएम पैड का रिकॉर्डर का चार्ट फट जाता था. So what I'm telling, we are not fooling anybody. So from operating practice to water chemistry, SWAS system is so well designed, but that's one of the neglected areas in almost all plants. And as rightly Dilip told, when we do a human test, the human reflexes will add a value, add error. So we have to trust. I remember a story. When he started in Singrauli, so first time the DS, data acquisition system, was put by the Westinghouse. And there were 2 school of operations, one GT batch, young batch, Another was the old people came from the private sector. So we used to see all those DCS readings and trained in the DOS. But we'll always be told, no, 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 वो कांटा वाला देख के चलाओ, ये गलत होता है. So I told, इसका list count 10 degree है, उसमें तो point में आ रहा है. नहीं, 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 तुम लोग को समझ में नहीं आता. And after 4 to 5 years, hardly anybody was seeing that dials, started believing. So everybody must start believing first in the online parameters. And when you'll believe, you validate it, make it correct. अभी सिलिका पे डाउट होता तो पहले जब मेजरमेंट देख लो, ये नहीं देखते कि भैया देखो कटायन कंडक्टिविटी बढ़ गई है क्या. First doubt we do on the measurement, human tendency. So let us mature all process and not only maintenance, operation, our layoffs, reservations, all are very critical. So let us standardize the process. We have experts with us, keep on engaging them. My all the best wishes. I think it's a very successful workshop. I'll request Munish and other Katreji to come out with a very detailed recommendation on the workshop, and our OND MTP team to track it, the implementation, give a feedback to expert and revise it so we are able to, if not 100%, go to 99 percentile of the implementation. Then again we'll work out. But I'll request each of us from JPL or from other. Today's world is analytics and diagnostics, not justifications and giving results. Then only will mature. So I again request and thanks to Dilip and Vinodji to come for and other participants from JSW, L&T, Adani for coming here. And we're looking after to create a community. At least within 50 kilometers, we have more than 30,000 megawatt plants. If I start from Jharsuguda, Gallipalli, and go up to Raipur, more than 30,000 megawatt plants. All different type of plants, BHL plants, Doosan, Harbin, Shanghai, Beijing, Benjong, Rallies, all manufacturing plants are there. So we have enormous knowledge. Let us simulate it. And in interest of us as a professional to get the professional satisfaction. So Manish has created a very right platform in the JIPT and the vision of Chairman Sir, that it should become the knowledge and hub of the knowledge center, providing knowledge and learning for serving society beyond the profits. So let us not look only for our plan, get the problem of others, create the solutions, and you are the best people for it. And you are the best faculties, best knowledge people. So all my best, and thank you very much for everybody for attending and giving me the chance to speak. Thank you very much.
Thank you very much for your valuable advice, sir. Now, the session for a distribution of mementos for the guests. I request our executive director to give memento to Dilip Singhania, sir. I request our to give Mr. Vinod Chaudhary, sir. I request our head of the plant to award gift to participants from Adani. Yes. No, sir. Mr. Abhishek.
L&T is there, sir.
Sir, Mr. Umar Ali, L&T developer. And may I request Mr. Manoj Shah from JSPL? Will I also chance? Tapas sir and madam. Hi, sir. Participants from JSW Charsaguda. Yes, please. Sir. I request our head of the plant to distribute this gift to JSW Charsaguda participants. Participants from OPJC, Bilpa. Oh, only one more, sir, OPJC. Thank you very much, sir. DB Power. Participants from DB Power. Thank you very much, sir. Now I request Mr. R.D. Katre, Vice President, to give vote of thanks.
Thank you, Karthikeyan sir. जैसे सर ने बोला कि really today I am overwhelmed by the response from you. काफी अच्छा लगा कि this is our third workshop of this year and जैसे मैं जो भी बोला था कि really I am thankful to our ED and HOP sir for his initiation or motivation to initiate this monthly workshop. Really, our first workshop was on coal, second was analytics, and third is on 2 days. And really, this is very good interactive sessions. Participants from the power plants, service providers, domain experts, as well as the academicians. In today's workshop, all were present. IIT Bhilai is ready to collaborate with us. L&T was there, and we all, the power sector, power professionals. Really, I am thankful to Vinod Chaudhary sir, Dilip Kumar sir, and all of you. Just as AD sir had told that it should not conclude here only, but we have to take takeaways from this conference. It will not be the theoretical only. It will convert into the business excellence. And in this line, we will, with our Mentors department from as well as the operation department, we will find out the takeaway points from this conference, what will be useful for our JPL and to other plants also. Yes, sir. Yes, sir. Yeah, that we have to widen our the participation base. Definitely. Thank you, sir. Really, sir. ये हमको पार्टिसिपेंट बेस और बढ़ाना है हमारा. दिस वर्कशॉप विल बी मोर इंक्लूसिव और हम लोग ऐसे ही वर्कशॉप करते रहेंगे on the important topics of the thermal power plants. And I would like to declare that the next workshop will be the best practices in thermal power plant in the flexibilization regime. Again, it will be sharing between us and it will standardize us. I am thankful to the participants who are present here, as well as who participated in online. There are so many participants who could not attend physically here, but they were available on the online. And all the presentations of this workshop will be shared with you, your organization, and it will. This discussion will not stop here. Rather, it is the opening of the discussion. If any of you any doubts or difficulties or explanation, you can directly contact to the presenters or via us. With these words, again, I am thankful to you. Thank you. Thank you very much. And let me this next workshop will be on 26th July. Because we have decided that the workshop, monthly workshop will be on the last week on Wednesday. Thank you. Thank you very much. Yeah, topic is the best practice in the thermal power plants in flexibilization regime. Thank you. Thank you very much.
Recording stopped.
अपना खुद का एक आइडिया है ना, काफी इशू का आइडिया है, अब खरीदने जाओगे ना तो किसी वाले किताब पढ़ने वाले कितने हैं?